Welcome to a place where learning meets relaxation. Take a deep breath and let your body sink into the comfort of your chair. Let the gentle rhythm of this tutorial start to wash over you. As we explore the world of shell programming, may your mind unwind and your worries fade away. Remember to like and subscribe to the channel for more soothing coding adventures. Let's begin. Understanding the importance of a properly configured shell environment is essential for anyone working with command line interfaces. A well-organized setup can significantly boost productivity by allowing users to streamline repetitive tasks, access frequently used commands quickly, and maintain a consistent workflow. Customizing the shell goes beyond mere aesthetics. It involves tailoring the environment to suit individual preferences and operational needs. This includes setting up aliases, defining custom functions, and integrating tools that enhance efficiency. Key components of shell configuration often involve environment variables, startup scripts, and prompt settings. By mastering these elements, users can create a personalized and powerful command line experience that adapts to their specific requirements. The shell environment is available in multiple versions, each with unique features and capabilities. Bash, the most widely used shell, offers a robust set of tools for scripting and command execution. CSH, known for its advanced features like auto-suggestions and theme support, is popular among power users. KSH, or Corn Shell, is valued for its compatibility with both Unix and Linux systems. To identify the shells installed on a system, users can run commands such as chsh-l or ls/bin/*sh. These commands list all available shells and their locations. Installing a new shell, such as ZSH on a Debian-based system, typically involves using a package manager like apt with the command sudo apt install ZSH. This process ensures the new shell is available for configuration and use. Changing the default shell is a straightforward process that allows users to switch between different shell environments. The command chsh-s followed by the full path to the desired shell, such as /bin/zsh, updates the user's default shell. After making this change, verifying the update with echo #shell confirms the new shell is active. It is crucial to ensure compatibility with existing scripts and tools, as some commands or configurations may behave differently across across shells. For example, a script written for Bash might not work as expected in ZSH without adjustments. Understanding these nuances helps prevent unexpected issues when transitioning between shell environments. Environment variables are a fundamental aspect of the shell environment, acting as placeholders for values that influence the behavior of programs and scripts. To define a variable, users can use the export command followed by the variable name and value, such as export var equals value. Common variables like path, which determines where the system looks for executable files, and home, which points to the user's directory, are critical for system operation. The user variable identifies the current user, while others like lang or tz affect locale and time settings. Viewing all environment variables can be done using commands like printenv or env, which display the complete list of active variables. These tools help users diagnose issues or customize their environment effectively. Shell configuration files play a vital role in defining how the shell behaves during startup. For Bash users, files like bashrc and bash profile are commonly used to set up aliases, functions, and environment variables. ZSH users, on the other hand, rely on ZSHRC for similar purposes. These files are typically located in the user's home directory and are executed automatically when the shell starts. Customizing these files allows users to automate tasks, such as setting up a personalized prompt or defining shortcuts for frequently used commands. To apply changes made to a configuration file, the source command followed by the file path, such as source hash, bashrc, reloads the settings without requiring a shell restart. The shell prompt, controlled by the PS1 variable, is a powerful tool for enhancing usability. By modifying PS1, users can customize the appearance of the prompt to include information such as the current user, host name, working directory, and even the exit status of the previous command. Adding colors and dynamic elements, like using escape sequences to highlight different parts of the prompt, can make the interface more intuitive. For example, exporting PS1 equals \u at \h:\w# creates a prompt that displays the username, host name, and current directory. Advanced users often leverage tools like ohmyzsh, which provides a collection of themes and plugins further personalize the shell experience. Managing shell history is an essential practice for tracking and reusing commands. The HISTSIZ variable controls the number of commands stored in the history list, while HISTFILE specifies the file where the history is saved. Configuring these variables in the shell's configuration file ensures that the history settings persist across sessions. The history command allows users to review previously executed commands, making it easier to recall or reuse them. Additionally, the HISTIGNORE variable can be used to filter out commands that are not needed in the history, such as repeated or insignificant entries. By fine-tuning these settings, users can maintain a clean and efficient command history that supports productivity and troubleshooting. Adopting best practices for shell setup ensures a stable and maintainable environment. Before editing configuration files, it is wise to create backups to prevent data loss or unintended changes. Avoiding clutter in global configuration files, such as those in the etc. directory, helps maintain system-wide consistency and reduces conflicts. For personal configurations, using version control systems like Git to track changes in dot files such as bashrc or cshRC provides a reliable way to manage and restore settings. These practices not only improve the reliability of the shell environment, but also make it easier to replicate configurations across different systems or share them with others. A well-configured shell is a cornerstone of efficient command line work, offering a tailored environment that aligns with individual needs and workflows. By customizing environment variables, prompts, and scripts, users can create a seamless and productive experience. Regularly reviewing and updating shell settings ensures that the environment remains optimized for current tasks and evolving requirements, whether through simple adjustments or advanced configurations. Taking the time to refine the shell setup can lead to significant improvements in performance, accuracy, and user satisfaction. Embracing these principles empowers users to harness the full potential of the command line. Welcome to this session on the fundamental principles of the shell programming language. Today, we will explore the basic commands and syntax that form the backbone of interacting with Unix-like systems. We will focus on tools essential for navigating the file system and managing files efficiently. Through practical examples files, you will gain a clear understanding of how these commands work in real-world scenarios. By the end of this presentation, you will have a solid foundation to build upon as we delve deeper into shell scripting. Let us begin by reviewing some of the most commonly used shell commands. The ls command lists the contents of a directory, providing a quick overview of files and subdirectories. The pwd command prints the current working directory, helping you understand your location within the file system. To move between directories, the cd command is indispensable. The echo command outputs text or the value of variables, often used for debugging or displaying messages. Creating new directories is straightforward with mkdir, while touch allows you to generate empty files. These commands are the building blocks for any task involving file management. Understanding the structure of shell commands is crucial for effective use. The general format is command options arguments. Options, which begin with a hyphen, modify the behavior of the command. For instance, lsl provides a detailed listing of files. Arguments specify the targets of the command, such as file names or directory paths. It is important to note that the shell is case sensitive, so ls and ls may produce different results depending on the environment. Always verify the exact case of commands and options to avoid errors. Shell commands often include options and arguments to customize their functionality. Short options like L, A, and H are single characters that can be combined, as seen in lslaw. Long options, such as help and version, are more descriptive and are often used for clarity, as in man help. Arguments can be files, directories, or specific values, such as in the cp command, where cp file 1, txt file 2, txt copies one file to another. Mastering these elements allows you to tailor commands to your specific needs. Input and output redirection is a powerful feature of the shell. The symbol redirects the output of a command to a file, overwriting its contents. For example, echo hello output. txt writes hello to a file named output.txt. The symbol reads input from a file, as demonstrated by cat input.txt, to display the contents of input.txt. The operator appends output to a file instead of overwriting it, making it ideal for logging or accumulating data. These techniques enable efficient handling of data flow within the shell. Combining commands through piping and chaining enhances productivity. The symbol or pipe takes the output of one command and uses it as input for another. For example, lsgrep txt filters the list of files to show only those with a txt extension. The operator allows you to execute multiple commands in sequence, such as cd/tmp, ls to change directories and list their contents. The end-to-end operator ensures that the next command runs only if the previous one succeeds, as in mkdir newdir and in cd newdir to create a directory and navigate into it. These tools enable complex workflows with minimal effort. In conclusion, we have covered the core commands for navigating and managing files, the structure of shell syntax, and techniques for redirecting input and output. By practicing these concepts, you will develop the skills to combine commands efficiently and automate tasks. The next session will build on this foundation by exploring advanced scripting and automation techniques. Remember, mastery of the shell comes with practice, so continue experimenting with these commands to deepen your understanding. The shell programming language provides powerful tools for managing files and directories, which are essential for automating tasks and interacting with the operating system. Efficiently handling files and directories allows users to organize data, streamline workflows, and perform complex operations with minimal effort. Key commands such as ls, which lists directory contents, cd, which navigates between directories, mkdir, which creates new directories, touch, which generates empty files, rm, which deletes files, cp, which copies files, and mv, which moves or renames files, form the foundation of these operations. Mastery of these commands is crucial for anyone working with shell scripting, as they enable precise control over the file system. Creating files in the shell can be done using the touch command, which generates an empty file, or the echo command, which adds specific content. Reading files is straightforward with cat, which displays the entire content, or less, which allows scrolling through large files. Writing to files involves appending text using echo with double greater than symbols, or overwriting with a single greater than symbol. Deleting files requires the rm command, which permanently removes them, so caution is necessary. Copying and moving files is handled by cp and mv, respectively, with the ability to specify source and destination paths. These operations are fundamental for managing data and are often combined in scripts to automate tasks. Directories serve as containers for organizing files, and creating them is done with mkdir. Navigating through directories is achieved using cd, which can move into subdirectories or return to the parent directory with cd. Listing directory contents is simple with ls, while lsl provides detailed information such as file sizes and permissions. Removing directories requires rmdir for empty ones, but non-empty directories necessitate the recursive option with rmr. Understanding these commands ensures that users can efficiently manage complex directory structures, which is vital for maintaining organized and functional file systems. File attributes and permissions determine how users interact with files and directories. The lsl command reveals permissions, ownership, and file types, such as regular files, directories, or symbolic links. Modifying permissions with chmod allows users to grant or revoke read, write, or execute access for the owner, group, or others. For example, chmod u+r adds read access for the user. Changing ownership with chown ensures that files are accessible to the correct users and groups. Recognizing these attributes is essential for security and collaboration, as they prevent unauthorized access and ensure proper resource management. Advanced file and directory management involves searching for files using find, which can locate files based on names, types, or other criteria. Combining commands through pipes, such as lsgrep, txt, allows filtering of output for specific information. Redirection with greater than and less than symbols enables controlling input and output, such as saving command results to a file. Wildcard characters like asterisk and question mark simplify pattern matching, making it easier to select multiple files or match specific names. These techniques enhance productivity by enabling precise and flexible interactions with the file system. By now, you should have a solid understanding of core file and directory operations in the shell. You can create, read, write, delete, copy, and move files and directories, as well as manage permissions and attributes. Advanced techniques like searching, piping, redirection, and wildcards further expand your capabilities. These skills are indispensable for writing effective shell scripts and automating tasks. As you continue practicing, you will gain confidence in using these tools to solve real-world problems, making you more efficient and versatile in system administration and software development. Shell variables are essential tools for storing and managing data within scripts and command line operations. They function as containers that hold values which can be referenced and manipulated throughout a script. One key characteristic of shell variables is their case sensitivity, meaning that a variable named name is distinct from a variable named name. This is important to remember to avoid unintended errors. By convention, shell variables are often written in uppercase letters to distinguish them from other elements in a script. Assigning a value to a variable follows a simple syntax where the variable name is placed directly before an equals sign, like this: variable name equals value. For example, the command name equals John assigns the string John to the variable name. This straightforward approach allows users to store and retrieve information efficiently. Shell variables come in two main types: local variables and environment variables. Local variables are defined within a specific script or shell session and are only accessible within that context. They do not affect other processes or sessions. In contrast, environment variables are available to all processes running in the system, including child processes spawned by the current shell. These variables are often used to configure the behavior of programs and scripts. To make a variable an environment variable, you use the export command. For instance, the command export myvar equals value converts the local variable myvar into an environment variable, allowing it to be accessed by any child processes. This distinction is crucial for understanding how data is shared across different parts of a system. Declaring and using shell variables involves a few key steps. When assigning a value to a variable, you must use the syntax variable equals value without any spaces around the equals sign. This is a common source of errors, so it is important to be precise. To access the value stored in a variable, you use the $sign followed by the variable name, like variable name, or the more explicit variable name. The latter is particularly useful when the variable is followed by other characters to avoid ambiguity. For example, if you set name equals Alice and then use the command echo hello name, the output will be hello Alice. This demonstrates how variables can dynamically insert values into commands and strings, making scripts more flexible and powerful. Environment variables are predefined by the system or set by the user and play a vital role in how the shell and applications operate. Common examples include path, which tells the system where to look for executable files, home, which points to a user's home directory, and user, which identifies the current user. These variables are accessible to all processes and can be viewed using commands like printenv or env. For instance, typing printenv in the terminal will display a list of all environment variables. Users can also modify these variables by using the export command or by editing configuration files such as bashrc. This allows for customization of the environment to suit specific needs or workflows. The scope and persistence of shell variables determine how they are used and shared across processes. Local variables are confined to the current shell session and are not passed to child processes. This means that if you define a variable in a script, it will not be available in any scripts or commands that the original script calls. Environment variables, on the other hand, are inherited by child processes and can persist across sessions if they are set in configuration files. For example, if you use the command export count equals 5, the variable count becomes available to any subshells or programs launched from the current shell. This makes environment variables ideal for settings that need to be consistent across multiple commands or scripts. Practical examples help illustrate how shell variables are used in real-world scenarios. A simple script might use a local variable to store a numerical value, such as pi equals 3, 14, and then display it using the echo command. This demonstrates how variables can hold and retrieve data within a script. Another example involves environment variables, where a script might export a variable like greeting equals welcome, and then use it in a message that includes the current user's name. The command echo greeting user would output something like welcome Alice if the user is Alice. These examples show how variables can enhance the functionality and adaptability of scripts by allowing dynamic content and configuration. When working with shell variables, there are several common pitfalls to avoid. One of the most frequent mistakes is including spaces around the equals sign in assignments, such as variable name equals value. This is invalid and will result in an error. To handle values that contain spaces, it is essential to use quotes like message equals hello world to ensure the entire string is treated as a single value. Additionally, variables that are no longer needed should be unset using the unset command to prevent them from interfering with other parts of a script. For example, unset myvar removes the variable myvar from the current session. These practices help maintain clean and reliable scripts by minimizing unexpected behavior. In summary, shell variables are fundamental to scripting and system interaction, providing a way to store and manipulate data. Local variables are confined to the current shell, while environment variables are shared across processes. Understanding how to declare, use, and manage these variables is essential for writing effective scripts. By practicing the declaration of variables, exporting them when necessary, and accessing their values, users can harness the full power of the shell to automate tasks and customize their environment. This knowledge is a cornerstone of proficiency in shell programming and enables more efficient and dynamic command line operations. Shell scripting is a powerful way to automate tasks using shell commands. It allows users to write sequences of commands in plain text files, which can then be executed by the shell. These scripts are incredibly useful for system administration, file management, and automation. Common shells include bash, CSH, and SH, each offering different features and compatibility. By learning shell scripting, you can streamline repetitive tasks and improve efficiency in managing your system. To create a script, you can use any text editor such as Nano or Vim and save the file with a SH extension. The first line of the script should be the shebang line, which is #bin/bash, followed by the commands you want to execute. After saving the file, you need to make it executable by using the chmod command with the +X option. Once the script is executable, you can run it by typing script name or by using the bash command followed by the script name. This process allows you to execute your script seamlessly within the shell environment. Variables in shell scripting are used to store data that can be referenced and manipulated throughout the script. You assign a variable using the equals sign, such as name equals John. To access the variable's value, you use the $sign followed by the variable name, like echo $name. The echo command is essential for outputting text or variable values to the terminal. Additionally, environment variables like home and user provide information about the user's environment, which can be accessed using the same $sign notation. Command substitution allows you to capture the output of a command and use it within a script. This is done by enclosing the command in parentheses, such as current date equals $open parenthesis, date close parenthesis. Alternatively, you can use backticks, though this method is less common. For example, you can store the current date in a variable and then display it using the echo command. This feature is particularly useful for dynamically inserting command outputs into your scripts. Control structures in shell scripting enable you to make decisions and repeat actions based on certain conditions. The if statement is used to execute commands conditionally, checking if a condition is true or false. Loops, such as for, while, and until, allow you to iterate over a set of commands multiple times. For instance, a for loop can process each file in a directory, making it easy to perform actions on multiple files at once. These structures add flexibility and power to your scripts, allowing them to handle complex tasks. Functions in shell scripting are blocks of code that can be reused throughout the script, promoting modularity and readability. You define a function by giving it a name followed by parentheses, then placing the code within curly braces. To call a function, you simply type its name followed by any arguments. Functions help organize your code, making it easier to maintain and understand. By breaking down your script into smaller, manageable functions, you can enhance both the efficiency and clarity of your work. Following best practices in shell scripting ensures that your scripts are reliable and easy to maintain. Always start your script with the shebang line #bin/bash to ensure portability across different systems. Adding comments throughout your script helps others and yourself understand the code's purpose. Validating inputs and handling errors can prevent unexpected issues, while keeping your scripts modular allows for easier updates and testing. These practices contribute to writing clean, effective, and robust shell scripts. In conclusion, shell scripts are a vital tool for automating repetitive tasks and improving system efficiency. Key components like variables, loops, conditionals, and functions form the foundation of effective scripting. By practicing with small scripts and tackling real-world tasks, you can build your skills and confidence. As you become more proficient, exploring advanced topics such as arrays and input handling will further expand your capabilities in shell programming. Shell scripts are text files that contain a sequence of commands that the shell can interpret and execute. These scripts are incredibly useful because they allow you to automate repetitive tasks, such as backing up files, managing system configurations, or performing batch processing. Instead of manually entering the same commands over and over, you can write a script once and run it multiple times. The shell, like bash or ZSH, acts as an interpreter for these scripts, executing each line in order. The benefits of using shell scripts include increased efficiency, as they can perform complex workflows in seconds, customization to fit specific needs, and the ability to automate routine operations, freeing up time for more creative or analytical tasks. To create a shell script, you can use any text editor, such as Nano, Vim, or Gedit. Begin by opening the editor and writing your commands line by line, just as you would type them directly into the terminal. A crucial step is adding a shebang line at the very top of the file. This line starts with a hash symbol, followed by the path to the interpreter, such as #bin bash, which tells the system which shell to use for executing the script. Once you've written your commands, save the file with a sh extension, like misscript, sh, to indicate that it is a shell script. This naming convention helps identify the file's purpose and ensures compatibility with the shell interpreter. After creating your script, you need to make it executable so that the operating system recognizes it as a runnable program. This is done using the chmod command, which modifies file permissions. The specific command is chmod +x followed by the script name, such as chmod +x misscript, sh. This grants the user execute permissions, allowing the script to run directly. To verify that the permissions have been set correctly, use the ls-l command, which displays the file's details, including its permissions. Additionally, always ensure that the shebang line at the top of the script points to the correct interpreter, as an incorrect path can prevent the script from running. Once your script is executable, you can run it by typing followed by the script name, such as /misscript, sh, in the terminal. This method works only if the script has execute permissions. If you don't have execute permissions, you can still run the script by specifying the interpreter explicitly, like bash miscrypt sh. When a script runs, it executes in the current shell or a subshell, depending on the commands it contains. The output of the script, such as messages or results, will appear directly in the terminal, making it easy to see the script's actions in real time. Variables in shell scripts are used to store and retrieve data, making scripts more flexible and dynamic. For example, you can declare a variable like name equals John, and then access its value using name, which would output John. This allows you to reuse values throughout the script without hard coding them. To interact with users, you can use the read command, which prompts for input and stores it in a variable, such as red name. This is useful for gathering information during script execution. Additionally, command line arguments like $1, $2, and so on allow scripts to accept input when they are run, enabling customization based on user input or external parameters. Conditional logic in shell scripts allows you to make decisions based on specific criteria, similar to how you might make choices in everyday life. The if statement is the primary tool for this, with the structure if condition then commands else commands phi. For example, checking if the current user is root by comparing user to root can trigger different actions. Conditions are tested using brackets, either or, with offering more advanced features. This flexibility enables scripts to handle various scenarios, such as verifying file existence, checking for errors, or adapting behavior based on input. By incorporating conditionals, scripts become more intelligent and responsive to different situations. Loops are essential for repeating tasks efficiently in shell scripts. A for loop iterates over a list of items, such as files in a directory, and performs an action for each. For instance, a for loop can echo the names of all txt files in the current directory. A while loop, on the other hand, continues executing as long as a condition remains true. This is useful for tasks like counting up to a specific number or processing data until a certain threshold is met. By using loops, you can automate repetitive actions without writing the same commands multiple times, making scripts more concise and easier to maintain. Functions in shell scripts allow you to group related commands into reusable blocks, improving code organization and readability. For example, a function named greet can take an argument and print a personalized message, like "Hello, Alice." This approach reduces redundancy, as you can call the function multiple times with different inputs instead of rewriting the same code. Functions also make scripts more modular, enabling you to break down complex tasks into smaller, manageable pieces. This not only simplifies debugging, but also makes the script easier to understand and update in the future. Debugging shell scripts is crucial for identifying and fixing errors. One method is using the set-x command, which traces each command as it executes, showing the script's progress and highlighting where issues might occur. Adding echo statements throughout the script can also help track variable values and the flow of execution. To check for syntax errors, the --n command tests the script without running it, catching mistakes like missing brackets or incorrect commands. Additionally, the trap command can be used to handle errors gracefully, ensuring the script responds appropriately to unexpected situations. These tools make debugging more efficient and less frustrating. Following best practices ensures that your shell scripts are reliable, maintainable, and easy to understand. Always include a shebang line at the top to specify the interpreter, preventing potential execution issues. Adding comments to explain complex sections of the script improves readability for others and your future self. Validating inputs, such as checking if a file exists or if a variable is set, helps prevent errors and unexpected behavior. Testing scripts in different environments ensures they work consistently across systems. Finally, keeping scripts modular by breaking them into functions or smaller scripts makes them easier to manage and adapt for future needs. In summary, shell scripts are powerful tools for automating tasks and boosting productivity. The key steps involve creating, making executable, running, and debugging scripts. Mastering variables, conditionals, loops, and functions allows you to tackle a wide range of tasks, from simple file management to complex system automation. By practicing and applying these concepts to real-world scenarios, you can develop scripts that save time, reduce errors, and streamline workflows. The more you experiment and refine your skills, the more proficient you'll become in harnessing the full potential of shell programming. Conditional statements are a fundamental aspect of programming that allows scripts to make decisions based on specific conditions. In the context of shell scripting, these statements enable programs to execute different sets of commands, depending on whether a given condition is true or false. The key keywords used in shell for this purpose are if else and phi. The if keyword starts the condition check. The else provides an alternative path if the condition is not met, and phi marks the end of the conditional block. These constructs are essential for creating dynamic and responsive scripts that can adapt to various scenarios. By evaluating expressions such as numeric comparisons or file checks, conditional statements ensure that the correct commands are executed at the right time. The syntax of the if statement in shell is straightforward, but requires careful attention to structure. The basic format begins with the if keyword followed by a test condition enclosed in square brackets. The test condition is evaluated, and if it returns a true value, the commands between then and phi are executed. The square brackets represent the test command, which checks the condition. It is crucial to remember that the test command requires spaces around the brackets. The then keyword signals the start of the block of commands that run when the condition is true. Finally, the phi keyword closes the if statement, ensuring the shell knows where the conditional block ends. This structure allows for precise control over the flow of a script. The else clause provides an alternative set of commands to execute when the if condition evaluates to false. This ensures that the script has a fallback option, making it more robust. For example, if a script checks whether a variable x is greater than 5, the else block can handle the case where x is 5 or less. The example given demonstrates this by printing different messages based on the value of x. The else clause is particularly useful for scenarios where two mutually exclusive outcomes are possible. It eliminates the need for additional if statements and keeps the code concise. By incorporating else, scripts can handle both true and false conditions systematically. When multiple conditions need to be evaluated, the logical operators A and O can be used to combine them. The operator functions as a logical AND, requiring both conditions to be true for the overall condition to succeed. The O operator acts as a logical OR, where at least one condition must be true. For instance, a script might check if x is greater than 5 and y is less than 10. However, it is important to note that these operators are specific to the test command and should not be used with the and or operators inside the square brackets. Instead, and can be used outside the test for command chaining. This distinction helps avoid confusion and ensures the correct evaluation of complex conditions. The elif clause, short for else if, allows for checking multiple conditions in sequence. This is particularly useful when there are more than two possible outcomes. For example, a script might first check if a variable is greater than 5, then if it is equal to 5, and finally, if it is less than 5. Each elif clause is evaluated in order, and the first true condition triggers its corresponding block of commands. This approach avoids nested if statements, making the code cleaner and easier to read. By using elif, scripts can efficiently handle a series of related conditions without complicating the structure. It is a powerful tool for creating multi-tiered decision-making processes. Common mistakes when working with conditional statements include forgetting to close the if block with phi, which leads to syntax errors. Another frequent issue is omitting spaces around the square brackets in the test command, causing the test to fail. Using the equals sign instead of ek for numeric comparisons can also produce unexpected results, because equals is for string comparisons. Additionally, failing to quote variables can lead to issues if the variable contains spaces or special characters. For example, if a variable holds a value with spaces, not quoting it might result in the shell interpreting the spaces as separate arguments. These pitfalls highlight the importance of paying close attention to syntax and proper usage of operators. Best practices for writing conditional statements in shell scripts include always closing if blocks with phi to maintain clarity and avoid errors. Quoting variables is essential to handle cases where the variable's value contains spaces or special characters, ensuring the script behaves as intended. Using and for command chaining outside the test command can improve readability and efficiency. Keeping conditions simple and avoiding overly complex expressions helps prevent logical errors. By adhering to these practices, scripts become more reliable, easier to debug, and maintainable over time. These habits contribute to writing clean and effective shell code. In conclusion, conditional statements are a cornerstone of shell scripting, enabling scripts to make decisions and adapt to different situations. Understanding their syntax and proper usage is crucial for creating reliable and efficient programs. By leveraging if-else and elif clauses, developers can build complex logic that handles multiple outcomes. Practicing with real-world scenarios helps reinforce these concepts and improves the ability to solve practical problems. As with any programming construct, mastering conditionals requires attention to detail and a commitment to best practices, ensuring that scripts perform as expected in various environments. Logical operators in shell scripting serve as the backbone for controlling the flow of execution based on conditions. These operators include and or and not, which are essential for creating logical expressions that determine the success or failure of commands. They are used in conjunction with commands, test expressions, or even pipelines to make decisions within a script. By utilizing these operators, you can create more dynamic and responsive scripts that handle various scenarios, making your shell programming more efficient and powerful. For instance, they allow you to chain commands together, ensuring that subsequent actions only occur if previous steps succeed or fail, which is crucial for automation and error handling. The and operator ensures that the second command runs only if the first command completes successfully. This is particularly useful for executing a sequence of commands where each step depends on the previous one. For example, if you want to create a directory and then navigate into it, you can use the and operator to ensure the second action only happens if the first is successful. This prevents errors that might occur if the directory creation fails. If any command in the chain fails, the entire sequence halts, which helps maintain script reliability. This operator is ideal for tasks that require a strict order of execution. The or operator executes the second command only if the first command fails. This is especially valuable for error handling, as it allows you to define alternative actions when a command does not complete successfully. For instance, if you are searching for a specific string in a file and it is not found, the or operator can trigger a message indicating the absence of the string. This provides a way to handle unexpected outcomes gracefully, ensuring that your script does not terminate abruptly. By using the or operator, you can create more robust scripts that adapt to different situations. The not operator inverts the exit status of a command, effectively negating its result. This is useful for creating conditions that depend on the absence of a particular state. For example, If you want to check that a file does not contain a specific line, the not operator can be used to reverse the outcome of a grep command. When paired with test commands, the not operator allows for more complex logical expressions, enabling you to write scripts that respond to a wide range of conditions. This flexibility makes it a powerful tool for crafting precise and nuanced decision-making logic. The test command, denoted by square brackets, evaluates expressions to determine their truth value. Common tests include checking for file existence, comparing strings, or verifying numeric conditions. For example, you can use the test command to check if a file exists and is readable before proceeding with further actions. This command returns an exit status of 0 if the condition is true and a non-zero value if it is false. By combining the test command with logical operators, you can create more sophisticated conditions that govern script behavior, allowing for precise control over program flow. Logical operators can be combined to create complex decision-making structures within a script. For instance, a sequence like command 1 and command 2 or command 3 will execute the third command if the first two fail. The order of evaluation is critical, with the and operator typically taking precedence over the or operator. This allows for nested conditions that can handle multiple scenarios simultaneously. Understanding how these operators interact is essential for writing efficient and readable scripts, as it enables you to implement multi-step logic that adapts to different runtime conditions. Practical examples illustrate the utility of logical operators in real-world scenarios. For instance, checking if a file exists and is readable can be done using a combination of test conditions and the and operator. This ensures that subsequent actions are only taken if both conditions are met. Another example is using the or operator to handle package updates, where the script attempts to update the package list and installs the package if the update fails. The not operator can also be used to skip actions under specific conditions, such as printing a message if a file does not contain a certain line. These examples demonstrate how logical operators enhance script functionality and reliability. Logical operators and test commands form the foundation of conditional execution in shell scripting. The and, or, and not operators allow you to create intricate decision-making structures, while the test command evaluates expressions to determine their truth value. Together, they enable scripts to respond dynamically to different situations, making them more versatile and efficient. Mastering these tools requires practice, particularly in applying them to real-world problems. By experimenting with different combinations and scenarios, you can develop a deeper understanding of how to leverage these operators to build robust and effective shell scripts. Loops are essential tools in shell scripting that allow you to automate repetitive tasks, saving time and reducing errors. By using loops, you can execute a set of commands multiple times without writing the same code over and over. There are 3 primary loop types in shell programming: for, while, and until. Each of these loops serves a distinct purpose based on the logic of iteration. The for loop is ideal when you have a fixed list of items to process. The while loop continues executing as long as a specific condition remains true. And the until loop runs until a condition becomes true. Understanding these differences will help you choose the right loop for your specific needs. The for loop is one of the most commonly used loops in shell scripting. Its syntax is straightforward. For variable in list, do command done. Here, the variable takes on each value in the list, and the commands inside the loop are executed for each value. For example, if you write for I in 1, 2, 3, do echo I done, the loop will print the numbers 1, 2, and 3. The for loop is particularly useful when you need to iterate over a fixed set of items, such as files in a directory, numbers in a sequence, or words in a list. You can also generate dynamic lists using command substitution, like for file in ls, do echo file done, which processes each file in the current directory. This makes the for loop a powerful tool for batch processing and automation. The while loop is designed to repeat a set of commands as long as a specific condition is true. Its syntax is while condition, do command, done. The condition is evaluated before each iteration, and if it is true, the commands inside the loop are executed. For instance, if you have a variable x initialized to 0 and write, while x is less than 5, do echo x, x equals $x plus 1 done, the loop will print numbers from 0 to 4. This type of loop is especially useful when the number of iterations is unknown beforehand. It is commonly used for monitoring dynamic data, such as checking system resources, waiting for user input, or processing real-time data streams. However, you must ensure that the condition eventually becomes false to avoid infinite loops. The until loop is similar to the while loop, but works in reverse. Its syntax is until condition, do command, done. Instead of running while the condition is true, the until loop continues executing until the condition becomes true. For example, if you write until f file txt, do sleep 1, done, the loop will keep checking for the existence of a file named file txt every second until it is found. This makes the until loop ideal for scenarios where you need to wait for a specific event to occur, such as a file being created, a service starting, or a network connection becoming available. Unlike the while loop, which runs while a condition is true, the until loop is perfect for situations where you want to keep trying until a desired state is achieved. Loop control statements give you greater flexibility in managing the flow of your loops. The break statement allows you to exit a loop immediately, regardless of the remaining iterations. For example, if you have a loop that processes numbers and want to stop when a certain value is reached, you can use break to terminate the loop early. The continue statement, on the other hand, skips the current iteration and moves to the next one. For instance, if you write for I in 1, 2, 3, do I is equal to 2, and in continue, echo I done, the loop will print 1 and 3, but skip 2. These control statements are invaluable for handling exceptions, optimizing performance, or avoiding unnecessary operations. By combining them with conditional checks, you can create more efficient and responsive scripts. In summary, the for loop is best suited for scenarios where you have a fixed number of iterations, such as processing a list of files or generating sequences. The while loop is ideal for situations where the number of iterations is unknown, like monitoring system status or handling user input. The until loop is particularly useful for waiting until a specific condition is met, such as a file being created or a service becoming available. Mastering these loops allows you to write more efficient and automated scripts, reducing manual intervention and increasing productivity. By understanding their unique use cases and control mechanisms, you can tackle a wide range of tasks in shell programming with confidence and precision. Case statements in shell scripting offer a powerful way to manage multiple conditions within a script. They function similarly to switch case constructs in other programming languages, allowing you to evaluate a variable against a series of patterns and execute corresponding commands. This approach is particularly useful when dealing with scenarios where a single variable might have several possible values, and you need to perform different actions based on those values. By leveraging case statements, you can write more organized and readable code compared to using nested if-else conditions. For instance, instead of writing multiple if-else blocks, a case statement can streamline the process by grouping related conditions together. This not only improves code clarity, but also makes it easier to maintain and debug. The key advantage of case statements lies in their ability to handle pattern matching, which allows for flexible and dynamic decision-making based on variable values. The syntax of case statements follows a specific structure that is both intuitive and easy to implement. It begins with the case keyword, followed by the variable you want to evaluate. The patterns you define are then listed with associated commands, each ending with a double semicolon to signal the end of that particular case. The general format is as follows: case variable in pattern 1 command 1, pattern 2 command 2, default command, SAC. Here, the variable is typically a shell variable, and the patterns can be exact matches or include wildcards. For example, a pattern like yes would match the input yes exactly, while a pattern like would match any input. The final pattern, denoted by an asterisk, acts as a default case to handle any unexpected values. This structure ensures that each pattern is evaluated in sequence, and once a match is found, the corresponding commands are executed. The use of double semicolons is critical to prevent unintended execution of subsequent cases, a feature known as fall-through. Understanding this syntax is essential for writing efficient and error-free shell scripts. Pattern matching in case statements is a fundamental aspect of their functionality, allowing you to define flexible conditions based on variable values. Wildcards such as asterisk, question mark, and brackets are commonly used to create patterns that match a range of possible inputs. The asterisk matches any sequence of characters, making it ideal for handling general cases. The question mark matches a single character, which is useful for scenarios where the input length is known. Brackets allow you to specify a set of characters, such as ABC, which matches any single character within the brackets. For example, If a script is designed to accept user input, a case statement might check for yes or no and provide specific responses. In the absence of a matching pattern, the default case handles unexpected inputs, ensuring the script remains robust. This ability to match patterns enhances the versatility of case statements, enabling scripts to adapt to various user interactions and system conditions. Advanced pattern matching in case statements expands the possibilities for conditional logic by incorporating ranges and negation. Ranges, such as a Z, allow you to match any lowercase letter, while 09 matches digits. Negation, denoted by an exclamation mark, enables you to specify patterns that exclude certain characters, such as 09 to match non-numeric values. These features are particularly useful for validating inputs or processing data with specific constraints. For instance, a script might use a Z to check if a user's input is a valid lowercase letter or -9 to ensure a string contains no numbers. By leveraging these advanced patterns, you can create more precise and efficient scripts that handle complex scenarios with ease. Additionally, combining ranges and negation allows for intricate matching rules, making case statements a powerful tool for tasks such as file type detection or system configuration checks. Case statements are widely used in practical scenarios where scripts need to interact with users, validate inputs, or automate tasks based on specific conditions. One common application is menu-driven scripts, where users can select options from a list, and the script executes corresponding actions. This approach enhances user experience by providing a structured way to navigate through different functionalities. Another key use case is input validation, where scripts check if user-provided data conforms to expected patterns. For example, a script might verify that a file name ends with a specific extension, or that a number falls within a certain range. Automation is another area where case statements shine, as they can trigger commands based on file types, system states, or other variables. By using case statements, scripts can efficiently handle diverse situations, reducing the need for repetitive code and improving overall performance. These practical applications demonstrate the value of case statements in creating versatile and reliable shell scripts. To ensure the effectiveness of case statements, it is essential to follow best practices that promote clarity and reliability. First, always always include a default case, denoted by an asterisk, to handle unexpected inputs. This prevents the script from failing silently and ensures that all possible scenarios are accounted for. Second, terminate each pattern with double semicolons to avoid fall-through, where the script might execute multiple cases unintentionally. This is crucial for maintaining the integrity of conditional logic. Third, keep patterns specific to prevent unintended matches. For example, using a broad pattern like might inadvertently match values that were not intended, leading to incorrect behavior. Instead, define precise patterns that align with the expected inputs. By adhering to these guidelines, you can create robust scripts that are easier to maintain and less prone to errors. These practices not only enhance the reliability of your code, but also contribute to a more efficient development process. In conclusion, case statements are an indispensable tool in shell scripting that simplify complex conditional logic and enhance flexibility through pattern matching. They provide a structured way to evaluate variables against multiple patterns, making scripts more organized and easier to read. The ability to match patterns allows for dynamic decision-making, enabling scripts to adapt to various inputs and situations. By mastering case statements, you can significantly improve the efficiency and readability of your shell scripts, leading to more reliable and maintainable code. Whether you are building interactive menus, validating inputs, or automating tasks, case statements offer a powerful solution that streamlines your workflow. As you continue to explore shell scripting, incorporating case statements into your repertoire will undoubtedly elevate your ability to create sophisticated and effective scripts. Functions in shell scripts are reusable blocks of code that help organize and structure your scripts more effectively. By grouping related commands into functions, you can make your code more modular, which means it's easier to understand, test, and maintain. Functions can take parameters, which are values passed to them when they are called, and they can also return values. Though in shell scripting, this is typically done through exit codes. Using functions reduces redundancy because you can write a piece of logic once and reuse it multiple times throughout your script, saving time and minimizing errors. To define a function in shell scripting, you can use one of two syntaxes. The first is function name, and the second is function name. Both approaches achieve the same result, but the first is more commonly used in traditional shell scripts. For example, a function called greet can be written as greet, echo, hello, $1, where $1 represents the first argument passed to the function. When you call a function, you simply use its name followed by any arguments you want to pass. For instance, calling greet world would output hello world. This makes functions a powerful tool for creating flexible and dynamic scripts. Arguments passed to functions are accessed using special variables like $1, $2, and so on, which represent the first, second, and subsequent arguments. The variable $0 holds the name of the function itself, which can be useful for debugging or logging purposes. The number of arguments provided to a function is stored in, which allows you to check how many parameters were passed. For example, a function called add can take two numbers and output their sum using $1 plus $2. This system of accessing arguments makes it easy to create functions that can handle a variety of input scenarios, enhancing the versatility of your scripts. In shell scripting, functions return an exit code to indicate whether they executed successfully. A return value of 0 typically means the function completed without errors, while a non-zero value signals an issue. You can explicitly set this exit code using the return command followed by a numeric value. For instance, a function called check can determine if the first argument is greater than 10 and return 0 if true or 1 if false. To check the exit code of a function, you can use, which stores the last command's exit status. This mechanism is essential for error handling and allows scripts to respond appropriately to different outcomes. Declaring variables inside functions with the local keyword helps prevent naming conflicts with variables in other parts of the script. When you use local, the variable is only accessible within the function's scope, reducing the risk of unintended modifications. For example, a function called calc can calculate the product of two numbers and store the result in a local variable. This practice ensures that variables like result do not interfere with other parts of the script, making the code more reliable and easier to debug. Using local variables is a best practice that contributes to cleaner and more maintainable shell scripts. When writing functions, it's important to follow best practices to ensure your scripts are efficient and easy to manage. Keep functions focused on a single task to avoid complexity and make them easier to test. Use descriptive names that clearly indicate what the function does, such as calculate sum instead of calc. Adding comments to document the purpose and behavior of functions helps others and yourself understand the code later. Finally, avoid overusing global variables, as they can lead to unpredictable behavior and make debugging more difficult. These practices lead to more readable, scalable, and robust shell scripts. Shell functions can be used to create more complex behaviors by calling other functions, processing multiple arguments, and handling optional parameters. For example, a function can call another function to perform a specific task, allowing for modular and reusable code. The shift command is useful for processing arguments in a loop, as it shifts the position of the arguments, making $1 the next argument each time. Handling optional parameters can be done by setting default values, ensuring the function works even if some arguments are missing. An example is a log function that formats messages with a timestamp or category, demonstrating how functions can be adapted to various use cases. Functions are a fundamental part of shell scripting that improve code reuse, readability, and maintainability. Understanding how to pass parameters, handle return values, and use local variables is crucial for writing effective scripts. By following best practices, such as keeping functions focused and well documented, you can create scripts that are easier to debug and expand. The ability to write modular functions allows you to build complex programs from smaller, manageable components. As you practice these concepts, you'll gain the skills needed to create efficient and reliable shell scripts that meet your specific needs. Input-output redirection is a fundamental concept in shell programming that allows you to control where data is read from or written to when executing commands. By default, every program in the shell interacts with 3 standard file descriptors. The first is standard input, which is typically the keyboard, where data is fed into a command. The second is standard output, which is usually the screen, where the program displays its results. The third is standard error, which also defaults to the screen, but is used specifically for error messages. These default behaviors can be modified using redirection operators, which enable you to direct input from files, send output to files, or capture error messages for further analysis. understanding how to manipulate these streams is crucial for managing data flow efficiently in shell scripts and command line operations. Each of these standard input, output, and error streams is represented by a unique number known as a file descriptor. The number 0 corresponds to standard input, 1 to standard output, and 2 to standard error. These file descriptors act as references for the system to track where data is coming from or going to. For example, when you type a command at the shell prompt, the input is read from file descriptor 0. When a command produces output, it is sent to file descriptor 1, and any errors are directed to file descriptor 2. By using redirection operators such as greater than, less than, and to greater than, you can modify these default file descriptors to point to different sources or destinations, such as files or other commands. This flexibility is essential for tasks like logging, debugging, and automating workflows. One of the most common uses of input-output redirection is to capture the output of a command and store it in a file. The greater than operator is used to redirect standard output to a file, overwriting its existing content. For instance, if you run the command echo hello greater than output txt, the text hello will be written to the file output txt, replacing any previous data in that file. On the other hand, the double greater than operator appends the output to the end of a file without erasing its contents. For example, the command ls double greater than file list txt would add the list of files in the current directory to the end of the file list txt. This is particularly useful for building logs or accumulating data over time without losing previous entries. Redirecting input allows you to provide data to a command from a file instead of typing it manually. The less than operator is used to read input from a file, which is especially helpful when working with commands that process large data sets or configuration files. For example, the command sort less than input txt would read the contents of input txt, sort them alphabetically, and display the result on the screen. This technique is commonly used in conjunction with commands like grep, awk, or sed to perform text processing tasks. By redirecting input, you can automate repetitive tasks and avoid the need to type the same data multiple times, making your workflow more efficient and less error-prone. Error messages are an important part of debugging and troubleshooting in shell scripting, and redirecting them to a file can help isolate issues. The to greater than operator is used to send standard error output to a specific file. For instance, if you run the command grep error log txt to greater than error log txt, any lines containing the word error in the file log txt will be displayed on the screen, while error messages generated by the command will be saved in error log txt. This separation of error messages from regular output is invaluable for monitoring and analyzing problems. Additionally, the to double greater than operator appends error messages to an existing file, allowing you to accumulate error logs over multiple runs of a command or script. In some cases, it is necessary to combine both standard output and standard error into a single stream for easier processing or logging. The ampersand greater than operator is a shorthand that redirects both standard output and standard error to the same file. For example, the command script sh ampersand greater than output txt would send all the normal output and error messages from the script to the file output txt. Another common technique is using to ampersand greater than 1 to redirect standard error to the same location as standard output. For instance, the command to ampersand greater than 1 greater than output txt would capture both the output and errors of the command in the file output txt. This is particularly useful when you want to monitor a command's behavior in real time, or when debugging complex scripts. The special file dev/null is often referred to as the null device because it discards all data written to it. This makes it a powerful tool for suppressing unwanted output. By redirecting standard output or error messages to /dev/null, you can prevent them from appearing on the screen or being saved to a file. For example, the command grep data file txt greater than dev/null would search for the word data in the file, but not display any results. This is useful in scenarios where you want to run a command silently, such as in automated scripts or background processes. Using dev/null helps keep the terminal clean and ensures that only relevant information is displayed, improving the overall user experience. Let me walk through some practical examples of how input-output redirection can be applied in real-world scenarios. For instance, the command ls s minus l greater than directory list txt saves the detailed listing of files in the current directory to a file named directory list txt. This is helpful for creating a snapshot of the directory structure. Another example is using the less than operator with the wc command, such as wc less than input txt, which counts the number of lines, words, and characters in the input txt file. When combining output and errors, the command compile sh2 ampersand greater than 1 pipe t build log captures both the standard output and error messages, displaying them on the screen while also saving them to build log. Finally, the command wget http://example.com2 greater than dev/null downloads a file from a URL without showing any error messages, which is useful when you want to suppress unnecessary output during automation. In summary, input-output redirection is a foundational skill for anyone working with shell programming. By mastering operators like greater than, double greater than, less than, and two greater than, you can efficiently manage data flow between commands, files, and the terminal. The ability to redirect standard output and error messages allows for better debugging and logging, while the use of /dev/null helps keep your environment clean by discarding unwanted output. Practicing these concepts with real-world examples will deepen your understanding and improve your ability to create robust and efficient shell scripts. As you continue to explore shell programming, these techniques will become second nature, enabling you to automate tasks and solve problems more effectively. Piping and command chaining are essential techniques for combining shell commands to create powerful and efficient workflows. By using pipes, you can take the output of one command and pass it directly into another, allowing for sequential processing of data. This is particularly useful when you need to filter, transform, or analyze information in a step-by-step manner. Command chaining, on the other hand, enables you to execute multiple commands in a single line, with the ability to control their execution based on success or failure. The logical operators and or allow you to build conditional logic, ensuring that commands run only when certain criteria are met. Together, these methods form the backbone of automation and data manipulation in shell scripts, making complex tasks manageable and reducing the need for intermediate files or manual intervention. The pipe operator is a fundamental tool in the shell that allows you to connect the output of one command to the input of another. Its syntax is straightforward, with the pipe symbol placed between two commands. For example, when you run ls-l pipe grep quat txt quat, the ls command lists all files in the current directory, and the grep command filters those results to display only lines containing the string quat txt quat. This creates a seamless flow of data where each command in the pipeline processes the output of the previous one. Pipes are especially useful for tasks like searching through large files, sorting data, or counting specific entries. By chaining commands in this way, you can perform intricate operations without the need for temporary files, making your scripts more efficient and easier to read. Command chaining with the and operator allows you to execute multiple commands in sequence, but only if each preceding command succeeds. The and operator ensures that the second command runs only if the first one completes without errors. For instance, if you run mkdir new folder and cd new folder, the cd command will execute only if the mkdir command successfully creates the folder. This is incredibly useful for building workflows where subsequent steps depend on the success of prior actions. It helps prevent errors from propagating through a script, ensuring that you don't attempt to perform an action on a non-existent directory or a failed process. By using and, you can create reliable scripts that handle dependencies and maintain a clean, error-free execution path. Command chaining with the or operator allows you to execute a second command only if the first one fails. This provides a way to handle errors gracefully by offering a fallback action. For example, if you run grep quat error quat log txt or echo quat no errors found quat, the echo command will execute only if the grep command does not find any lines containing quat error quat. This is particularly useful in scenarios where you want to log an issue or take an alternative action when a command doesn't produce the expected result. The or operator adds resilience to your scripts, ensuring that even if a command fails, the script can still proceed with a defined response. This makes your scripts more robust and adaptable to unexpected situations. Combining pipes and chaining allows you to create complex workflows that process data and handle errors in a single line of commands. For example, the command cat data txt pipe grep quat user quat pipe wc-l and echo quat count complete quat demonstrates how data flows through a series of commands. The cat command reads the file. The grep filters for lines containing quat user quat, and the wc counts those lines. The and operator ensures that the echo command runs only if the entire pipeline succeeds. This approach enables you to build multi-step processes without writing separate scripts or intermediate files. By nesting pipes and chains, you can create efficient, readable, and maintainable scripts that handle both data transformation and error handling in a streamlined manner. Practical use cases for piping and command chaining are abundant in real-world scenarios. For instance, filtering logs with journoctal pipe grep quat fail. Quat allows you to quickly identify system failures without sifting through irrelevant information. Counting specific entries such as ps aux pipe grep quat python quat pipe wc-l helps you determine how many Python processes are running at a given time. Conditional file operations like cp file txt backup slash or echo quat copy failed quat ensure that you are notified if a copy operation fails. These techniques are invaluable for automating repetitive tasks, reducing manual effort, and improving the efficiency of system administration and data processing. By leveraging these tools, you can create scripts that handle complex operations with minimal code. To make the most of piping and command chaining, it is important to follow best practices that enhance readability and reliability. Keeping commands simple and modular ensures that each part of your script has a clear purpose, making it easier to debug and maintain. Using the set -e option in your scripts can help you exit immediately if any command fails, preventing cascading errors. Combining pipes with the T command allows you to both display and save the output of a command, which is useful for logging and debugging. However, it is crucial to avoid overly complex chains that may become difficult to understand or maintain. By striking a balance between functionality and clarity, you can create scripts that are both powerful and easy to work with. In conclusion, piping and command chaining are fundamental concepts in shell scripting that empower users to create efficient, automated, and error-resilient workflows. Pipes enable enable the seamless transfer of data between commands, allowing for powerful data processing and transformation. Command chaining with and/or adds logical control, ensuring that commands execute only when necessary and handling errors gracefully. Mastering these techniques not only enhances your ability to automate tasks, but also improves your problem-solving skills in the shell environment. Whether you are filtering logs, managing files, or building complex scripts, these tools are essential for anyone looking to harness the full potential of the command line. Command substitution is a powerful feature in shell scripting that allows the output of a command to be used as an argument or value within another command or variable. This capability enables scripts to dynamically insert values generated by other commands, making them more flexible and responsive to changing conditions. For example, instead of hard-coding a date or a file name, you can let the shell handle it dynamically. There are two primary methods for achieving this: the command syntax, which is modern and widely preferred, and the older backtick syntax, which is still functional but less commonly used. Understanding both methods is essential for writing efficient and maintainable shell scripts. The command syntax is the modern and recommended approach for command substitution. It allows the output of a command to be seamlessly integrated into a string or another command. For instance, if you want to display the current date within a message, you can use echo "today is date." Here, the date command runs, and its output replaces the date portion. This method is particularly useful for embedding dynamic values into strings. Additionally, the command syntax supports nested commands, meaning you can place one command substitution inside another. For example, echo result, echo date would first execute the inner date to get the date, and then pass it to the outer echo command. This nesting capability makes command more versatile and easier to read compared to older methods. The backtick syntax, denoted by command, is an older method for command substitution that functions similarly to command. For example, echo "today is date" produces the same result as the date example. However, backticks are less readable, especially when dealing with nested commands or complex scripts. Consider a scenario where you need to nest multiple commands: echo result, echo date. The backticks can become confusing and harder to track, leading to potential errors. Moreover, backticks may require additional escaping with backslashes in certain situations, which can complicate scripts. While they are still supported in most shells, their use is generally discouraged in favor of the more modern command syntax. There are several key differences between the command syntax and backticks that influence their usage. First, readability. Command is easier to read, particularly when dealing with nested commands or complex expressions. Second, compatibility. Both methods work in most shells, but command is more widely supported in modern environments. Third, escape characters. Backticks can sometimes require escaping with backslashes, which can introduce errors if not handled carefully. Finally, modern practice. The command syntax is strongly recommended for its clarity, flexibility, and ease of use. By adopting command, you ensure your scripts are more maintainable and less prone to errors, especially in collaborative or long-term projects. Command substitution has numerous practical applications in shell scripting. One common use is assigning the output of a command to a variable. For example, today equals $date stores the current date in the variable today, which can then be used elsewhere in the script. Another application is integrating command output into file paths. For instance, cat find /tmp name log would read the contents of files matching the log pattern in the /tmp directory. Additionally, command substitution can combine with other commands to build more complex operations. An example is echo files, lslgrep txt, which lists all txt files in the current directory by piping the output of lsl to grep. These examples demonstrate how command substitution enhances the functionality and adaptability of shell scripts. Command substitution is particularly useful in scenarios requiring dynamic values. For instance, scripts that generate timestamps or retrieve system information can benefit from embedding command output directly into their logic. When building complex commands, you can chain multiple subcommands together, with each step's output feeding into the next. For example, using find and grep in combination with command substitution allows for efficient file searches. Additionally, command substitution is ideal for passing the output of one command as an argument to another. This is especially helpful when automating tasks that depend on real-time data, such as processing log files or handling user input dynamically. These use cases highlight the importance of mastering command substitution for creating robust and efficient shell scripts. To ensure clarity and reliability in your scripts, follow best practices when using command substitution. First, prefer the command syntax over backticks for better readability and nesting capabilities. Avoid overcomplicating scripts by using too many layers of substitution, as this can reduce maintainability. Always test command substitution in isolation to verify that the output is correct and behaves as expected. For example, run the command separately before integrating it into a larger script. Additionally, use quotes to handle cases where the command output might contain spaces or special characters. For instance, echo LSL ensures that the entire output is treated as a single argument, preventing unexpected behavior. These practices help create more robust and error-free shell scripts. In summary, command substitution and backticks are fundamental tools for creating dynamic and responsive shell scripts. While both methods serve the same purpose, the command syntax is the preferred choice for modern, maintainable scripts due to its readability and flexibility. Understanding the differences between the two methods allows you to make informed decisions based on your script's needs. Whether you're automating tasks, handling dynamic data, or building complex commands, command substitution is an essential skill for any shell programmer. By mastering these techniques, you can write more efficient, reliable, and adaptable scripts that meet the demands of real-world applications. Error handling is a critical aspect of writing reliable shell scripts. Without proper error handling, scripts can fail silently or produce unexpected results, leading to difficult-to-diagnose issues. Understanding how commands fail and return exit codes is essential for building robust automation. In this session, we will explore techniques to manage errors effectively, interpret exit codes, and ensure scripts respond appropriately to failures. By the end of this training, you will be equipped to handle errors with confidence and improve the stability of your shell scripts. Every command executed in a shell script returns an exit code, which is a numeric value that indicates the success or failure of the command. A 0 value typically means the command executed successfully, while any non-zero value signals an error. Common exit codes include one for general errors, 2 for misuse of commands, 126 for command not found, 127 for invalid commands, and 130 for scripts terminated by Control plus C. These codes serve as a universal language for scripts to communicate their status, allowing for automated error detection and response. The special variable $? Or in shell scripting stores the exit code of the last command executed. This variable is invaluable for checking the success or failure of commands within a script. For example, if you run a command that is expected to fail, such as listing a non-existent directory, the variable will capture the exit code, which in this case is 2. By checking the value of after critical commands, you can make informed decisions within your script, such as logging errors or exiting gracefully. Conditional error checking is a fundamental technique for managing errors in shell scripts. Using the if statement, you can execute different blocks of code based on the success or failure of a command. For instance, if you attempt to list a directory and it fails, the else clause can trigger an error message. This approach allows for precise control over script behavior. Additionally, the logical operators and/or can streamline error handling. For example, using command 1 and command 2 will execute the second command only if the first succeeds, while command 1 or command 2 will execute the second if the first fails. These tools enable concise and readable error management. The set-e option is a powerful tool for automatic error handling in shell scripts. When enabled, this option causes the script to exit immediately if any command returns a non-zero exit code. For example, if you set-e and then run a command that fails, the script will terminate without executing subsequent commands. While this can prevent cascading failures, it requires caution, as it may skip critical steps that need to be executed regardless of previous errors. Use this option judiciously, especially in scripts where certain actions must occur even if earlier steps fail. The trap command provides a way to execute specific actions when a script encounters an error or exits. By using trap with the signal, you can define a command to run whenever any command in the script fails. For example, trap echo error occurred. Will print an error message whenever a command fails. This is particularly useful for cleanup tasks, such as removing temporary files or logging errors before the script terminates. Combining trap with other error handling techniques ensures that your scripts can respond gracefully to unexpected issues. In addition to standard exit codes, you can define custom exit codes to represent specific error scenarios in your scripts. For instance, using exit 10 might indicate a file not found error, while exit 20 could signal a configuration issue. Custom codes allow for more precise error reporting, but it is essential to document them clearly and use them consistently across your scripts. This practice improves maintainability and makes it easier for others to understand and debug your code. Always ensure that custom codes align with your script's logic and requirements. Common error scenarios in shell scripts include missing files, permission issues, and invalid commands. For example, if a script attempts to search for a pattern in a file that does not exist, the grep command will fail, and the script can use an exit code to signal this issue. By incorporating exit codes into your scripts, you can provide clear feedback about the nature of the error. For instance, using grep pattern file txt, exit 1 allows the script to terminate immediately if the command fails, preventing further execution that might depend on the successful completion of grep. Adhering to best practices for error handling ensures your scripts are both reliable and maintainable. Always check the exit codes of critical commands to verify their success before proceeding. The set -e option can automate this process, but it should be used with care to avoid skipping necessary steps. Combining trap with set -e enhances error recovery by allowing cleanup or logging before the script exits. These practices work together to create robust scripts that handle failures gracefully and provide meaningful feedback for debugging and improvement. Effective error handling is a cornerstone of writing reliable shell scripts. Exit codes provide critical feedback that enables scripts to respond to failures and maintain stability. By mastering techniques such as set -e, the $? Variable, and the trap command, you can create scripts that are resilient to errors and easier to debug. As you continue to develop your skills, remember that consistent error handling not only improves script reliability, but also enhances the overall user experience by reducing unexpected behavior. With practice, these concepts will become second nature, allowing you to build more sophisticated and dependable automation. Debugging is a critical process in shell scripting that helps identify and resolve errors to ensure scripts run as intended. When writing shell scripts, errors can take various forms, such as syntax errors, which occur when the script violates the rules of the shell language. Logical errors happen when the script runs without crashing, but produces incorrect results due to flawed logic. Runtime errors arise during execution, often caused by external factors like missing files or invalid commands. By mastering debugging techniques, you can enhance the reliability and maintainability of your scripts, making them easier to update and troubleshoot in the future. Debugging shell scripts can be challenging due to several common pitfalls. One frequent issue is unintended variable expansions or missing quotes, which can lead to unexpected behavior when variables contain spaces or special characters. For example, a variable with a space might split into multiple arguments if not properly quoted. Incorrect file paths or permissions can also cause scripts to fail silently or produce errors. Additionally, unexpected exit codes from commands can be tricky to trace, as they may indicate failures that are not immediately visible. Logical errors in loops, conditionals, or function calls can be particularly difficult to spot, as they often require careful inspection of the script's flow and data handling. Several tools and techniques can aid in debugging shell scripts. The set-x option enables trace mode, which displays each command as it is executed, allowing you to see the exact steps the script is taking. This is particularly useful for tracking down where a script might be deviating from expected behavior. The set-e option causes the script to exit immediately if any command returns a non-zero exit code, which helps catch errors early. The set-u option treats unset variables as errors, preventing silent failures that can occur when a variable is accidentally left undefined. Additionally, the --n option allows you to perform a syntax check without running the script, which is ideal for catching syntax issues before execution. Echo statements are a simple yet powerful way to debug shell scripts. By inserting echo commands, you can print the values of variables or track the flow of execution. For example, using echo current directory, pwd helps confirm the script's working directory at a specific point. Another useful technique is the set -v option, which prints each command as it is read by the shell. This can be especially helpful for understanding how the script is parsing its input and where potential issues might arise. Combining echo statements with these options provides a clear view of the script's behavior, making it easier to pinpoint problems. For more complex scripts, using a debugger like bashdb can significantly streamline the debugging process. Bashdb allows you to execute scripts step by step, inspecting variables and control flow at each stage. Commands such as break set breakpoints to pause execution at specific lines. Step allows you to move through the script line by line. Print displays the value of variables or expressions, and continue resumes execution until the next breakpoint. This level of control is invaluable for diagnosing intricate logic errors or understanding how nested loops or functions interact. While bashdb is not always necessary for simple scripts, it becomes a powerful tool for tackling more sophisticated shell programs. Adopting best practices for debugging can save time and reduce frustration. Testing scripts incrementally by adding functionality step by step helps isolate issues as they arise, rather than trying to debug an entire script at once. Using version control systems like Git allows you to track changes and revert to previous versions if a bug is introduced. Logging outputs to files provides a record of the script's behavior, which is useful for analyzing issues that occur in production environments. Finally, reviewing scripts with peers offers fresh perspectives and can uncover overlooked errors or inefficiencies. These practices, when combined, create a robust approach to debugging and script development. In conclusion, debugging is an essential skill for any shell scripter, as it ensures scripts are reliable, efficient, and easy to maintain. By leveraging tools like set-x, bash-n, and bashdb, you can diagnose and resolve issues more effectively. Prioritizing clarity and modularity in your scripts makes troubleshooting simpler, as well-structured code is easier to understand and modify. Regular practice with debugging techniques builds confidence and improves the overall quality of your shell scripts. Remember, the more you debug, the more proficient you become in writing error-free and robust shell programs. Good day. Today, we will delve into advanced variable manipulation in the shell programming language. This topic is essential for creating efficient and dynamic scripts. We will explore techniques that allow you to manage and modify variables in sophisticated ways. By mastering these methods, you can significantly enhance the performance of your scripts. The focus will be on string operations, arithmetic calculations, and array handling, which are fundamental to solving complex programming challenges. These skills will empower you to handle data more flexibly and write more robust code. Let us now discuss variable substitution techniques. One powerful method is substring extraction using var offset length. This allows you to retrieve specific parts of a string by specifying the starting position and the number of characters. For example, if you have a variable containing a file name, you can extract the extension using this syntax. Additionally, we will look at prefix removal with var pattern and var pattern. The former removes the shortest matching pattern from the beginning, while the latter removes the longest matching pattern. Similarly, var %pattern and var %% pattern are used for suffix removal, helping you clean up or parse strings efficiently. These techniques are invaluable for tasks like parsing log files or manipulating file names. Next, we will examine string manipulation in the shell. One common task is replacing patterns within a string. The syntax var/pattern/replacement replaces the first occurrence of a pattern, while var/pattern/replacement performs a global replacement, changing all instances. This is useful for modifying text data, such as adjusting configuration files or formatting output. Another powerful feature is case conversion. Using var transforms the entire string to uppercase, while var converts it to lowercase. These operations can be applied to variables containing user input or data from external sources, ensuring consistency in your scripts. Arithmetic expansion is a critical tool for performing calculations within shell scripts. The syntax expression allows you to evaluate mathematical expressions. For example, you can add, subtract, multiply, or divide variables directly. Increment and decrement operators like var++ and ++var are also available, providing flexibility in loops and counters. Additionally, you can combine arithmetic operations with variable assignments, such as result equals $A plus B, which simplifies complex calculations. These features make it easy to handle numerical data and perform dynamic computations within your scripts. Working with arrays is another key aspect of shell programming. Arrays allow you to store multiple values in a single variable, making it easier to manage collections of data. To access individual elements, use array index, where index refers to the position in the array. The length of an array can be determined with array_at, which is useful for iterating through all elements. When looping through arrays, the syntax for element in array_at ensures that each item is processed correctly, even if it contains spaces or special characters. These operations are essential for tasks like processing lists of files or user inputs. Associative arrays, also known as hash maps, provide a way to store key-value pairs. Unlike regular arrays, which use numeric indices, associative arrays use strings as keys. To declare an associative array, use declare a map. Accessing values is straightforward with mapKey, where key is the string identifier. Iterating over keys in an associative array can be done with for key in, map at, do, done, allowing you to perform operations on all stored data. This structure is particularly useful for managing configurations, mappings, or any scenario where you need to retrieve values based on unique identifiers. As we conclude, let us review best practices and common pitfalls. Always quote variables to prevent issues like word splitting and globbing, which can lead to unexpected behavior. For example, using var ensures that the variable's value is treated as a single unit. Avoid using eval unless absolutely necessary, as it can introduce security risks and make code harder to debug. Instead, use declare to enforce variable types, such as declare I for integers, which ensures that only numeric values are assigned. These practices will help you write safer and more maintainable scripts. In summary, mastering advanced variable manipulation techniques is crucial for writing efficient and flexible shell scripts. By applying these methods, you can handle complex data structures and implement dynamic logic with ease. Real-world examples, such as parsing logs, processing user inputs, or managing configurations, will help solidify your understanding. Practice is key to proficiency, so I encourage you to experiment with these techniques in your own projects. With dedication, you will become adept at leveraging shell variables to solve a wide range of programming challenges. Arrays in the shell programming language allow you to store multiple values within a single variable, making it easier to manage related data. Indexed arrays use numeric keys starting from 0, which means each element is accessed by its position in the sequence. To create an indexed array, you use the syntax array equals value 1, value 2, value 3. For example, the command fruits equals apple, banana, cherry creates an array named fruits containing 3 elements. This structure is particularly useful for grouping items like file names, command outputs, or arguments that need to be processed together. Accessing elements in an array is done using their index numbers. The syntax arrayIndex retrieves a specific element, such as fruits1, which would output banana. To get all elements of an array, you can use arrayAt, which expands to each item individually. This is especially helpful when iterating over the array. Additionally, the expression arrayAt provides the number of elements in the array, which is useful for determining the size of the data set. For instance, if you have 3 elements, this would return the value 3. These tools allow you to dynamically interact with the data stored in arrays. Modifying arrays involves adding, removing, or updating elements. To add a new value, you can use the syntax array plus equals newValue, which appends the element to the end of the array. For example, fruits plus equals date adds date to the fruits array. Removing an element is done with the unset command, such as unset array2, which deletes the element at index 2. Updating a value is straightforward. Just assign the new value to the desired index, like array1 equals grape, to change banana to grape. These operations make arrays flexible for handling changing data. Looping through arrays is a common task in shell scripting. A for loop can iterate over each element using the syntax for fruit in fruitset do echo fruit done. This ensures that each element is processed individually, even if the elements contain spaces. For scenarios where you need to track the index, a while loop can be used with a counter variable. For example, I equals 0, while I lt fruitset do echo fruits $I equals $I plus 1 done. This approach allows you to access both the index and the value, which is useful for tasks like modifying elements based on their position. Associative arrays are a powerful feature that allows you to use string keys instead of numeric indices. This makes them ideal for mapping relationships, such as usernames to IDs or configuration settings. To declare an associative array, you use the command declare a array name. For example, declare a colors red FF creates an array called colors with a key red and a value of a hexadecimal color code. Unlike indexed arrays, associative arrays provide more flexibility when the data is naturally grouped by names rather than positions. Accessing values in an associative array is done using the key names. The syntax array key retrieves the corresponding value, such as colors red, which would output FF0. To list all the keys in an associative array, you can use array at, which expands to each key individually. This is useful for iterating over the array or checking the available keys. For example, if you have keys red and blue, this syntax would return those strings, allowing you to process them in loops or other operations. Modifying an associative array involves adding, updating, or removing key value pairs. To add a new entry, you simply assign the key and value, like array key equals value. Updating an existing value is the same process, just use the same key with the new value. To remove a key, you use the unset command, such as unset array key. These operations make associative arrays highly adaptable for dynamic data structures, such as storing user preferences or configuration settings that may change over time. Looping through an associative array allows you to process both the keys and their corresponding values. A for loop can iterate over the keys using the syntax for key in, colors at do echo key, colors $key done. This is particularly useful for displaying or manipulating all the entries in the array. For example, if the colors array contains red and blue, the loop would output red, FF0 and blue, 0 FF. This approach is efficient for tasks like generating reports or applying changes to all entries in the array. Arrays are commonly used for storing lists of files, command outputs, or arguments that need to be processed collectively. For example, you might use an array to store a list of file names and then loop through them to perform actions like renaming or backing up. Associative arrays, on the other hand, are ideal for mapping string keys to values, such as usernames to user IDs or error codes to to messages. Combining arrays with loops enables dynamic data processing, allowing scripts to handle varying amounts of data efficiently. This flexibility makes arrays and associative arrays essential tools for automating tasks in shell scripting. In summary, arrays provide a way to organize multiple values using numeric indices, making it easy to manage sequential data. Associative arrays extend this functionality by allowing string keys, which are better suited for complex mappings. Loops and commands like array at or declare a help manipulate and access elements efficiently. Choosing between indexed and associative arrays depends on the nature of the data and the specific requirements of the task. By understanding these structures, you can write more powerful and efficient shell scripts. Regular expressions are patterns used to match character combinations in text. They are essential for text processing in shell scripting because they allow you to search, modify, and extract data efficiently. Regex simplifies tasks like searching for specific words, replacing text, or pulling out information from large files. For example, you can use regex to find all instances of a particular error message in a log file, or to clean up data by removing unwanted characters. Common tools that utilize regex include grep, which searches for patterns, sed, which edits streams of text, awk, which processes data based on patterns, and find, which locates files using regex-based criteria. These tools are fundamental in automating workflows and handling text-based tasks in the shell environment. The basic syntax of regular expressions includes meta characters, which have special meanings. Examples of meta characters are the dot, which matches any single character, the asterisk, which denotes 0 or more occurrences of the preceding element, the plus, which indicates 1 or more occurrences, the question mark, which matches 0 or 1 occurrence, square brackets, which define character classes, the caret, which anchors the match to the start of a line, the $sign, which anchors the match to the end of a line, and the pipe, which acts as an OR operator. Literals, on the other hand, are exact characters that you want to match, such as the word hello, which will only match the string hello. Character classes allow you to specify a set of characters to match, like ABC, which matches any one of a B or C ranges, such as a Z. Enable you to match any lowercase letter, while 09 matches any digit. Anchors like the caret and $sign are crucial for ensuring that patterns match specific positions in a line, such as the beginning or end of a string. In the shell, you can use regular expressions with various commands to manipulate text. The grep command searches for patterns within files. For instance, if you run grep error log txt, it will display all lines in the log file that contain the word error. The sed command is a stream editor that can perform substitutions on text. An example is sed's old new file, txt, which replaces the first occurrence of old with new in each line of the file. The awk command allows you to process text based on patterns, such as printing lines that match a specific condition. For example, awk pattern print $0 data. txt will print all lines in data txt that contain the specified pattern. These tools are powerful when combined with regex, enabling you to perform complex text transformations and data extraction tasks directly from the command line. Regular expressions have numerous practical applications in shell scripting. For example, filtering logs is a common task where you might use grep 404 access log to find all lines in an access log that indicate a 404 error. Extracting data from a file can be done by combining grep with other commands like cut. For instance, grep IP data txt cut d. F1 would extract the first field from lines containing the word IP. Replacing text in a file is another key use case, where said old new G file txt replaces all occurrences of old with new in the file. Validating input, such as checking if a phone number follows a specific format, can be achieved with more complex regex patterns. For example, grep E0-9320-94 phone txt ensures that each line in the phone txt file matches a pattern like 123.4.56.70.890. These examples demonstrate how regex can streamline tasks that would otherwise require more complex scripting. When working with regular expressions, there are several common pitfalls to avoid. One key issue is escaping characters, as certain symbols like the dot or asterisk have special meanings. To match a literal dot, you must use a backslash, such as backslash, in your pattern. Another consideration is the difference between basic and extended regex flavors. By default, the shell uses basic regular expressions, but you can enable extended regex by using the E option with commands like grep. Testing your patterns is crucial, and you can use commands like echo or cat to debug them by piping sample text into your regex. For example, echo hello grep hello helps verify that your pattern matches as expected. Additionally, maintaining readability in your scripts is important, especially when dealing with complex patterns. Adding comments to explain your regex can make your code easier to understand and maintain for others or yourself in the future. Regular expressions are a powerful tool for text manipulation in the shell environment. Mastering patterns allows you to automate tasks more efficiently, reducing the need for manual intervention and improving script reliability. By practicing with real-world examples, such as parsing log files or validating data formats, you can build proficiency in crafting effective regex patterns. It is essential to test your patterns thoroughly before deploying them in production environments to avoid unintended behavior. As you become more familiar with regex, you will find that it becomes an indispensable part of your shell scripting toolkit, enabling you to handle a wide range of text processing challenges with ease. Good day. Today, we will explore 3 essential command line utilities for text processing: grep, sed, and awk. These tools are fundamental in the world of shell scripting and system administration. Grep is designed to search for specific patterns within files, making it ideal for filtering information. Sed, short for stream editor, allows for basic text transformations on the fly, such as replacing or deleting content. Awk is a powerful tool for pattern scanning and processing, capable of handling complex data manipulation tasks. Together, these utilities form a robust toolkit for working with text in the Unix environment. Let us begin with grep. The basic syntax is straightforward: grep pattern file name. This command searches for the specified pattern in the given file. For example, grep error log txt will display all lines containing the word error. However, grep offers several options to enhance its functionality. The I option ignores case, so grep I error log txt will match both error and error. The V option inverts the match, showing lines that do not contain the pattern. The C option counts the number of matching lines, which is useful for quick statistics. For instance, grep I error log txt will find all case-insensitive matches, while grep C success output txt will count how many times the word success appears. Now let us delve into advanced grep features. Regular expressions are a powerful way to define patterns. The caret symbol denotes the start of a line, so grep start will find lines beginning with the word start. Similarly, the dollar symbol marks the end of a line, as in grep end dollar to find lines ending with end. Recursive searches are also possible with grep r keyword directory, which searches for the keyword in all files within the specified directory. Additionally, counting lines with grep c success. Output txt provides a quick way to assess the frequency of specific terms in a file. These features make grep a versatile tool for both simple and complex text analysis tasks. Next, we turn to sed, the stream editor. Its syntax is sed command file name. Sed processes text line by line, applying commands to each line. One of the most common commands is sold new, which replaces occurrences of old with new. For example, seds hello hi input. Txt will replace the first instance of hello with hi in each line of input, txt. Other commands include d to delete lines and I\text to insert text before a line. These operations allow for efficient text manipulation without modifying the original file, making sed ideal for quick edits or preprocessing tasks. Sed's capabilities extend further with multiple commands and address ranges. By using the E option, you can apply several commands in sequence, such as sed E, AB, ECD, to replace a with B and C with D in the same file. Address ranges let you target specific lines, like sed start end D, to delete all lines between the markers start and end. In-place editing is another feature, achieved with the I option, as in sed I's old new file, txt, which directly modifies the file instead of outputting to the terminal. These advanced features make sed a flexible tool for handling complex text transformations. Now let us introduce awk, a powerful pattern scanning and processing tool. Its syntax is awk pattern action file name. The pattern specifies the condition to match, and the action defines what to do when the condition is met. For example, awk print $1 data. Txt will print the first field of each line in data, txt. Awk also provides built-in variables like $0 for the entire line and $1, $2 for individual fields. Conditional processing allows for more dynamic actions, such as awk $3 $100, print $0, file txt to display lines where the third field exceeds 100. These features make awk particularly useful for analyzing structured data, such as log files or spreadsheets. Combining grep, sed, and awk creates a powerful workflow for text manipulation. By piping the output of one tool to another, you can filter, transform, and analyze data in stages. For instance, grep error log txt sets error critical. Awk print $2 first filters lines containing error, then replaces error with critical, and finally prints the second field of each line. This approach is invaluable for processing large datasets or log files, where each tool handles a specific task. Use cases include extracting specific information from structured text, automating report generation, or troubleshooting system issues by isolating relevant data. In conclusion, grep, sed, and awk are indispensable tools for text processing in the shell. Grep excels at pattern matching and filtering. Sed handles stream-based transformations, and awk provides advanced data processing capabilities. By mastering these tools individually and learning to combine them, you can tackle a wide range of text manipulation challenges. Whether you are analyzing logs, cleaning data, or automating tasks, these utilities offer efficiency and flexibility. Embrace their power to streamline your workflow and unlock new possibilities in command line operations. Text processing involves manipulating and analyzing text data in the shell. This includes tasks like searching for specific information, modifying content, or extracting relevant parts of a file. Filtering, on the other hand, refers to selecting specific lines or patterns from input, which is crucial for narrowing down large data sets. Key tools in this area include grep, sed, awk, sort, and unique. These utilities are essential for log analysis, where you might need to identify errors or trends. Data extraction, such as pulling specific fields from a dataset, and automation, where scripts can process text dynamically. Understanding these tools allows you to handle both structured and unstructured data efficiently. The key commands for text processing are grep, sed, awk, sort, and unique. Grep is used to search for patterns in files or input, making it ideal for locating specific strings or regular expressions. Sed acts as a stream editor, enabling you to perform text transformations like substitutions, deletions, or insertions. Awk is a powerful pattern scanning and processing language, often used for analyzing and manipulating data in a structured format. Sort organizes lines of text alphabetically or numerically, while unique helps identify or remove repeated lines. Together, these commands form the backbone of many shell-based data workflows. The basic syntax for grep is grep options pattern file. Options like I make the search case insensitive. R allows recursive searches in directories, and V inverts the match to show lines that do not contain the pattern. For example, using grep error log, txt will display all lines in the file log txt that include the word error. Combining grep with a pipe allows you to chain commands, such as filtering results further with sort or unique. This flexibility makes grep a versatile tool for quickly isolating relevant information from large data sets. The syntax for sed is sed options script file. Common operations include substitution, where you replace text using the S pattern replacement command, deletion to remove lines, and insertion to add new content. For instance, the command sed old new G file txt replaces all occurrences of old with new in the file. Using the I option edits the file in place, which is useful for modifying configurations or data files directly. Sed's ability to process text line by line makes it a powerful tool for batch editing tasks. Awk is a pattern scanning and processing language that operates on a line-by-line basis. Its syntax is awk pattern action file, where the pattern defines the condition and the action specifies what to do when the condition is met. Variables like $1 and $2 refer to the first and second fields in a line, while NF indicates the total number of fields. For example, awk print $1 data. txt prints the first column of data. Awk also supports conditional logic, arithmetic operations, and even user-defined functions, making it suitable for complex data analysis tasks. Sorting and unique filters are handled by the sort and unique commands. Sort organizes lines alphabetically by default, but using the N option sorts numerically. Unique removes duplicate lines, with options like D to show only duplicates and C to count their occurrences. For example, combining sort and unique as sort file, txt unique D identifies repeated lines in the file. The R option with sort reverses the order, which is useful for viewing data from last to first. These tools are essential for cleaning and analyzing datasets. Pipelines allow you to combine commands using the pipe symbol, creating a chain where the output of one command becomes the input of the next. For instance, grep error log txt sort unique C counts occurrences of error messages. This approach enables efficient data flow, reducing the need for intermediate files. Tools like zargs can further extend pipelines by passing output as arguments to other commands. Pipelines are a cornerstone of shell scripting, allowing you to perform complex transformations with minimal effort. Practical examples of text processing include extracting specific data from logs, such as using awk print $1 access.log to find IP addresses associated with 404 errors. Another use case is filtering and counting email domains by extracting the domain part with cut D at F2 emails txt, then sorting and counting unique entries. Removing blank lines from a file can be done with said D file txt. Automating report generation often involves combining grep, sort, and awk to process data dynamically. Demonstrating the power of these tools in real-world scenarios, text processing and filtering are critical for handling both structured and unstructured data in the shell. Mastering tools like grep, sed, awk, sort, and unique significantly enhances shell scripting efficiency, allowing you to automate repetitive tasks and analyze large datasets. Pipelines enable complex data transformations with minimal commands, making workflows more streamlined. Practicing with real-world scenarios helps reinforce these skills, ensuring you can apply them effectively in various professional contexts. Good day, everyone. Today, we will explore the essential best practices for writing shell scripts. These guidelines are designed to help you create scripts that are not only efficient, but also easy to read, understand, and maintain over time. Consistency in your code is crucial because it allows you to and others to navigate and modify scripts without confusion. Security is another key aspect, as even small oversights can lead to vulnerabilities. Portability ensures your scripts work across different systems and environments, which is vital for collaboration. By following these best practices, you reduce the likelihood of errors and make teamwork more seamless. Let's dive into the details of each of these principles. When writing shell scripts, the way you structure and format your code plays a significant role in its readability. For example, using descriptive variable names like maxaritris instead of generic names like X makes your intentions clear to others and yourself. Comments are equally important. They help explain complex logic or steps that might not be immediately obvious. Imagine a script that performs a series of nested loops and conditional checks without comments. Even the author might struggle to recall the purpose of each step. Proper indentation and spacing also contribute to clarity. A well-formatted script is easier to debug and modify, which is especially helpful when multiple people work on the same project. Error handling is a critical component of any robust script. When a command fails, it often returns an exit code that indicates the nature of the problem. By checking these exit codes using or the operator, you can take appropriate actions, such as logging an error or terminating the script gracefully. The set E command ensures your script stops immediately if any command fails, preventing cascading errors that might be harder to trace. Additionally, using trap allows you to define cleanup routines that execute when the script is interrupted, such as when a user presses Ctrl+C. These practices make your scripts more reliable and easier to manage in unpredictable environments. Security should never be overlooked in shell scripting. One common pitfall is using the eval command with untrusted input, which can lead to code injection attacks. For example, if a script processes user-provided data and uses eval without validation, an attacker could inject malicious commands. Quoting variables is another essential practice. When you use var, you prevent unintended word splitting and globbing, which can alter the behavior of commands. Finally, restricting file permissions with chmod ensures that only authorized users can execute or modify sensitive scripts. These measures protect your scripts and the systems they run on from potential threats. Portability is key when writing scripts that need to work across different systems and shells. Using POSIX-compliant syntax ensures compatibility with a wide range of environments, from traditional Unix systems to modern Linux distributions. Avoiding shell-specific features, such as bash-only constructs like arrays or advanced pattern matching, can prevent unexpected behavior when the script is run elsewhere. Testing your scripts in different environments, such as comparing sh and bash, helps identify and resolve compatibility issues early. By prioritizing portability, you make your scripts more versatile and future-proof. Modularity and reusability are fundamental to writing clean and efficient shell scripts. Breaking your script into functions allows you to organize code logically, making it easier to test and maintain. For instance, a function that handles user input can be reused across multiple scripts. Sourcing external files or functions also promotes code reuse, reducing redundancy. Hard-coding values, such as file paths or configuration parameters, make scripts less flexible. Instead, using parameters or environment variables allows users to customize behavior without modifying the script itself. This approach enhances adaptability and simplifies updates. Testing and validation are essential for ensuring your scripts behave as expected. Writing unit tests for critical functions helps catch bugs early, especially in complex logic. Validating input parameters, such as checking for required arguments or ensuring data formats are correct, prevents errors that could arise from unexpected inputs. Tools like setx enable debugging by printing each command as it is executed, while bash n checks for syntax errors without running the script. These practices help you build confidence in your scripts and reduce the risk of failures in production environments. Documentation is often overlooked, but plays a vital role in the maintainability of your scripts. A well-documented script includes a header that explains its purpose, author, and usage. This information is invaluable for others who might need to modify or extend the script. Documenting functions with descriptions and parameters clarifies their roles and expected inputs. It's also important to keep comments up to date when code changes, as outdated documentation can be misleading. Proper documentation saves time and reduces the likelihood of errors during future modifications. Version control and collaboration are critical when working on scripts with others. Storing scripts in a version control system like Git allows you to track changes, revert to previous versions, and collaborate effectively. Meaningful commit messages provide context for each change, making it easier to understand the evolution of the script. Consistent naming conventions for scripts and files also improve organization, especially in large projects. By following these practices, you ensure that your scripts are easier to manage, review, and integrate into larger workflows. To recap, the best practices we've discussed: readability, error handling, security, modularity, testing, documentation, and collaboration are foundational to professional shell scripting. These principles not only enhance the quality of your scripts, but also make them more reliable and easier to work with over time. As you continue to develop your skills, remember that adhering to standards and continuously learning from experience will help you write better scripts. By applying these practices, you contribute to a more efficient and secure computing environment. Thank you for your attention. Command line arguments are inputs that users provide to a script when they run it. These arguments allow scripts to behave differently based on the context in which they are used. For example, a script that processes files can take different file names as arguments, making it versatile. Special variables like $1, $2, dollar at dollars, and help scripts access and manage these arguments. $1 refers to the first argument, $2 to the second, and so on. And at both represent all arguments, but they behave differently when quoted. Gives the total count of arguments passed. These variables are essential for building dynamic and reusable scripts. The $0 variable holds the name of the script itself, which is useful for displaying help messages or logging. $1, $2, and so on represent the positional arguments provided by the user. For instance, if a script is called with 3 arguments, $1 would be the first, $2 the second, and $3 the third. The variable tells you how many arguments were passed, which is critical for validating input. Dollar and at both list all arguments, but treats them as a single string, while at preserves each argument as a separate element. Understanding the difference between these two is key to avoiding bugs in scripts that process multiple arguments. Parsing arguments effectively requires techniques like the shift command, which moves the positional parameters left by 1, allowing scripts to iterate through arguments. Case statements are useful for matching patterns in arguments, such as handling different command line options. The getOps utility is specifically designed for parsing options like V or H, making it easier to handle flags and their associated values. Combining these methods allows for complex argument handling, such as supporting both positional arguments and optional flags. For example, a script might use getOps to process V for verbose mode, and then handle a additional positional arguments. Validating input is crucial to ensure scripts handle unexpected or missing arguments gracefully. For instance, checking if is 0 might trigger a usage message. Using get-ups ensures structured parsing of options, reducing errors from malformed input. Providing clear usage messages helps users understand how to run the script correctly. Avoiding hard-coded assumptions about argument order or count makes scripts more robust. For example, a script that expects exactly 3 arguments should check and inform the user if the count is incorrect. These practices improve the reliability and usability of shell scripts. An example of using command line arguments is a script that adds 2 numbers. By accessing $1 and $2, the script can perform arithmetic operations like $1 plus $2. However, this approach requires careful handling of input types. Another example is a script that uses get-ups to parse options like V for version or H for help. This allows users to customize the script's behavior. The at variable is useful for passing all arguments to another command, preserving their individuality. For instance, a wrapper script might use at to forward arguments to a different program, ensuring flexibility in how commands are executed. Command line arguments are a powerful tool for making scripts adaptable and efficient. Proper parsing techniques ensure that scripts can handle a wide range of inputs without errors. Mastering variables like at, get-ups, and shift enables advanced scripting capabilities, such as handling complex workflows or user-defined options. These skills are fundamental for creating scripts that are both functional and user-friendly. By applying best practices and understanding the nuances of argument handling, scriptwriters can build robust solutions that meet diverse needs. Good day. Today, we will explore the foundational elements of the shell environment and how initialization files shape the user experience. Understanding environment variables is essential because they store critical configuration data that influences both the shell and the processes it runs. These variables act as a communication bridge between the operating system and applications. We will also delve into the purpose of shell initialization files, which are scripts that execute automatically when a shell session starts. These files allow users to tailor their environment, from setting up custom commands to defining the look and feel of the terminal. By the end of this session, you will know how to personalize your shell to suit your workflow. Environment variables are key value pairs that hold information about the system and user settings. For example, the path variable specifies directories where the shell should search for executable files. The home variable points to the user's home directory, while user identifies the current login name. The editor variable determines the default text editor for the shell. These variables can be accessed using the echo command, followed by the variable name in $signs, such as echo path, or the printenv command to list all variables. They play a vital role in controlling how programs behave and how user sessions are configured. Modifying these variables can change the way applications interact with the system, making them a powerful tool for customization. Shell initialization files are scripts that run automatically when a shell session starts. These files are crucial for setting up the environment and defining user-specific configurations. Common initialization files include bash profile, bashrc profile, and zshrc, depending on the shell being used. Each file serves a specific purpose. For instance, bash profile is typically used for login shells, such as when logging in via SSH, while bashrc is for interactive non-login shells, like terminal windows. These files can contain commands to set environment variables, create aliases, or define functions, allowing users to automate tasks and streamline their workflow. In Bash, the key initialization files include bash profile, bashrc profile, and zshrc for ZSH users. The bash profile is executed for login shells, meaning it runs when you log in through a terminal or SSH. The bashrc file is used for interactive non-login shells, such as when opening a new terminal window. The profile file serves as a fallback on some systems and is often sourced by bash profile. For users of the ZSH shell, the zshrc file is the primary configuration file. Each of these files has a distinct role in initializing the shell environment, and understanding their differences ensures that configurations are applied correctly. The way initialization files function depends on the type of shell session. Login shells, such as those started via SSH, read the bash profile or profile file. Interactive shells, like those launched from a terminal window, typically load the bashrc or CSHRC file. These files contain scripts that set environment variables, define aliases, and configure the shell's behavior. For example, a script might add a directory to the path variable or create a custom alias for a frequently used command. Changes made to these files take effect after the shell is sourced, which can be done manually using the source command or by restarting the shell session. Editing initialization files requires a text editor such as Nano, Vim, or Gedit. For example, the command nano bashrc opens the bash rc file for editing. Before making changes, it is wise to back up the original file to prevent accidental loss of configurations. Once edits are made, the changes can be applied immediately by sourcing the file using the source command or the dot command, such as source /bashrc. This avoids the need to restart the shell, allowing users to test configurations in real time. Always verify the syntax of the file to ensure there are no errors that could disrupt the shell's functionality. Customizing the shell environment involves various techniques. Aliases allow users to create shortcuts for complex commands, such as defining LL as LSL for a more readable directory listing. Functions can be used to encapsulate multiple commands into a single, reusable command. Environment variables can be modified to extend the path or set other system-wide settings. For instance, adding a new directory to the path enables the shell to recognize commands in that location. Prompt customization changes the appearance of the shell prompt, making it more informative or visually distinct. These customizations enhance productivity by tailoring the shell to the user's preferences. Troubleshooting initialization files involves checking for syntax errors and debugging scripts. The bash n command can be used to check for syntax issues without executing the file. The setx option enables debugging by printing each command as it is executed, helping to identify problematic lines. To maintain a clean and efficient configuration, avoid duplicating settings across multiple files. Keeping initialization files minimal and well organized reduces the risk of conflicts and makes them easier to manage. Regularly reviewing and testing configurations ensures that the shell remains stable and responsive to user needs. In summary, environment variables and initialization files are fundamental to shaping the shell experience. They provide the tools to customize the environment, automate tasks, and improve workflow efficiency. By mastering these concepts, you can create a shell environment that reflects your specific needs and preferences. Practice is key. Experiment with editing and testing configurations in real-world scenarios to build confidence and proficiency. With time, you will be able to leverage these tools to enhance your productivity and control over the command line. Sourcing scripts is a fundamental concept in shell programming that allows you to execute commands within the current shell session rather than in a separate subshell. This means that any changes made to variables, functions, or the environment during the sourcing process remain active in the parent shell. Unlike running a script directly, which spawns a new subshell and isolates its changes, sourcing preserves the state of the current shell. Common scenarios where sourcing is particularly useful include loading environment variables, defining reusable functions, or applying configuration settings that need to persist across multiple commands or scripts. This technique is especially valuable when you want to maintain a consistent shell environment without restarting the session. The dot command is a key tool for sourcing scripts in the shell. It is represented by a single period followed by the script name, such as script sh. Alternatively, you can use the source command, which is functionally identical and often preferred for readability. Both methods effectively execute the script's contents in the current shell context, as if the commands were typed directly into the terminal. This is distinct from running a script with the notation, which creates a new subshell. The dot command and source command are particularly useful when you need to modify the current shell's state, such as setting environment variables or defining functions that should be available immediately. When you source a script, the shell reads and executes each line of the script in the current shell session, rather than in a separate process. This line-by-line execution ensures that any modifications to variables, functions, or the environment are retained after the script finishes running. For example, if a sourced script defines a function, that function remains accessible in the parent shell. Similarly, if the script exports a variable, that variable persists in the current session. This behavior makes sourcing ideal for reusing code across multiple scripts, or for setting up a consistent environment. By sourcing scripts, you avoid the need to duplicate code and maintain modular and efficient workflow. The distinction between sourcing and executing a script is critical for understanding how shell commands behave. When you execute a script using the notation, it runs in a new subshell, and any changes made to variables or the environment are confined to that subshell. Once the script completes, those changes are discarded. In contrast, sourcing a script using the dot command or source command runs the script in the current shell, allowing changes to persist. For instance, if a script sets an environment variable, that variable remains available after sourcing, but would be lost if the script were executed normally. This difference is essential for tasks like configuring the shell, defining functions, or managing settings that need to be shared across multiple commands. To illustrate how sourcing works, let's consider a practical example. Suppose you create a script called env.sh with the following content: export myvar equals hello. When you source this script using the command source env.sh, the shell reads the export statement and sets the myvar variable in the current session. You can then verify the result by typing echo myvar, which will output hello. This demonstrates how sourcing allows variables to be retained in the shell. If you had executed the script instead of sourcing it, the variable would not be available afterward. This example highlights the practical application of sourcing for managing environment variables and ensuring they are accessible across different parts of your workflow. When working with sourced scripts, it's important to follow best practices to ensure reliability and security. First, always use absolute paths when sourcing scripts to avoid ambiguity or unintended execution of scripts from unexpected locations. Second, avoid sourcing scripts that have side effects, such as modifying files or altering system settings, unless you are certain of their impact. These actions can lead to unpredictable behavior or conflicts. Additionally, ensure that sourced scripts have the correct permissions, such as being executable with chmod +x to prevent errors or security risks. By adhering to these guidelines, you can leverage sourcing effectively while minimizing potential issues in your shell environment. In summary, sourcing scripts and using the dot command are essential techniques for maintaining and sharing shell state across commands and sessions. Understanding the difference between sourcing and execution is crucial for writing effective and reliable shell scripts. Sourcing allows changes to persist in the current shell, making it ideal for configuration and reuse, while execution isolates changes in a subshell. By applying best practices, such as using absolute paths, avoiding scripts with side effects, and managing permissions, you can ensure that your scripting practices are both secure and efficient. These principles will help you harness the full power of shell scripting in your workflows. Shell scripts are powerful tools that can automate complex tasks, but their power comes with responsibility. If not handled with care, they can introduce serious vulnerabilities that compromise system integrity. Security considerations are essential to prevent unauthorized access, data breaches, and system compromise. For example, a poorly written script might inadvertently grant access to sensitive files or allow malicious actors to execute arbitrary commands. Key areas to focus on include input validation, which ensures that user-provided data is safe and predictable; permissions, which control who can access or modify scripts; command injection, which involves preventing malicious input from executing unintended commands; and secure coding practices that minimize risks from the start. Common security vulnerabilities in shell scripts often stem from oversight in handling user input and system resources. Command injection is one of the most critical risks, where attackers inject malicious commands through untrusted input. For instance, if a script uses user-provided data directly in a command, an attacker could exploit this to run harmful code. Improper permissions are another issue, as scripts with overly permissive access rights, such as 777, allow unauthorized users to modify or execute them. Hard-coded credentials, like storing passwords in plain text within scripts, expose sensitive information to anyone with access to the file. Unvalidated inputs can lead to unexpected behavior, such as buffer overflows or unintended command execution, making it crucial to sanitize all data before processing. To write secure shell scripts, validation of all inputs is non-negotiable. This involves using regular expressions or whitelists to ensure that inputs conform to expected patterns. For example, a script expecting a file name might reject any input containing special characters. Avoiding the use of eval is another critical practice, as it can execute arbitrary code and open the door to injection attacks. Instead, use safer alternatives like parameter expansion or built-in commands. Minimizing privileges means running scripts with the least necessary permissions, reducing the potential damage if a vulnerability is exploited. For dynamic input, prefer the red command over eval, as it allows safer handling of user input without executing it as code. Protecting sensitive data in shell scripts requires proactive measures. Hard-coding secrets like passwords or API keys in scripts is a major risk, as these can be exposed through version control or file access. Instead, use environment variables or encrypted files to store such data, ensuring they are not visible in the script itself. Secure temporary files should be created using mktemp, which generates unique names and prevents race conditions, limiting the script's access to only necessary resources, such as specific files or directories, reduces the attack surface. When logging information, avoid storing sensitive data in plain text and consider using encryption or obfuscation to protect it. Input validation techniques are essential for ensuring that scripts behave predictably. Using case statements or regular expressions allows you to define acceptable input patterns. For example, a regex like AZ0-9 ensures that input contains only alphanumeric characters and underscores. Checking for unexpected characters or patterns helps detect malicious input before it causes harm. An example of this is using the input $=AZ0-9 condition in a script to validate a username. Rejecting invalid inputs with clear error messages not only improves security, but also enhances user experience by guiding users toward correct input. Preventing command injection requires careful handling of user-provided data. Never pass untrusted input directly to commands, as this can lead to unintended execution. Instead, use arrays to store command arguments, which prevents shell expansion and ensures that inputs are treated as separate parameters. For example, cmd=echo input is safer than cmd=echo input because it avoids issues with spaces or special characters. When possible, prefer built-in shell features over external commands, as they reduce the risk of injection and improve performance. This approach also limits the script's reliance on external tools, which may have their own vulnerabilities. Setting appropriate permissions for scripts is a fundamental security practice. Using chmod 700 ensures that only the owner can read, write, and execute the script, while chmod 750 allows the owner and group members to access it. Avoid using setuid or setchid unless absolutely necessary, as they can escalate privileges and create security risks. Regularly auditing script permissions with commands like find or lsl helps identify and fix overly permissive settings. Additionally, avoid using sudo in scripts unless required, as it grants elevated privileges that can be exploited if the script is compromised. Secure use of external commands involves validating and sanitizing all arguments to prevent unintended behavior. For example, if a script uses user input to construct a command, it must ensure that the input does not contain malicious elements. Avoiding the source or .command with untrusted files prevents unintended execution of arbitrary code. Using exec to execute commands ensures that the script does not create unnecessary child processes, which can be a security risk. Finally, restrict script execution to trusted environments, such as controlled directories or isolated containers, to minimize exposure to potential threats. Prioritizing security in shell scripts is essential to prevent exploits and breaches that can have far-reaching consequences. By validating inputs, minimizing privileges, and avoiding unsafe practices like eval or hard-coded credentials, you can significantly reduce risks. Tools like ShellCheck provide static analysis to identify potential vulnerabilities in your code. Staying updated on security best practices for shell scripting ensures that your scripts remain resilient against evolving threats. Remember, security is not a one-time task, but an ongoing commitment to writing robust, secure code. Functions in shell scripting are powerful tools that allow you to create reusable code blocks, which can be called multiple times throughout a script. This not only reduces redundancy, but also makes your code easier to maintain and update. Advanced features such as parameters, return values, and nested functions take these functions to the next level. Parameters enable functions to accept input, making them dynamic versatile. Return values allow functions to communicate results back to the main script, while nested functions let you build complex logic by combining smaller, focused functions. These elements are crucial for creating modular and maintainable scripts, as they break down large problems into manageable pieces. By using functions effectively, you can significantly improve the efficiency and readability of your shell scripts, making them more robust and easier to debug. In shell scripting, positional parameters such as $1, $2, and so on represent the arguments passed to a function. These are essential for making functions adaptable to different inputs. The special variables at and $, are used to handle all the arguments provided to a function. While it preserves each argument as a separate entity, $, treats them as a single string. This distinction is important when you need to process arguments individually or as a group. Passing arguments to functions is straightforward. Just list them after the function name. However, handling variable numbers of arguments requires careful consideration. For example, you might use a loop to iterate over at and process each argument dynamically. Understanding these mechanisms allows you to write flexible functions that can handle diverse scenarios. Returning values from functions in shell scripting is a nuanced process. The return statement is used to send an integer exit code, typically between 0 and 255, to indicate the success or failure of a function. However, this is limited to numeric values. To return more complex data, such as strings or arrays, you can use echo or printf. For instance, a function might output a message or a result that can be captured using command substitution, like result equals $function. This allows the main script to use the returned value for further processing. It's important to note that shell scripting has limitations in returning non-integer values, so developers often rely on output redirection or global variables for more sophisticated data exchange. Mastering these techniques ensures that functions can effectively communicate with the rest of the script. Nested functions are a powerful feature that allows one function to call another, enabling the creation of complex workflows. When functions are nested, the scope of variables becomes critical. By default, variables are global, meaning they can be accessed and modified by any part of the script. However, using the local keyword within a function restricts variable scope to to that function, preventing unintended side effects. This is especially important in nested functions, where multiple layers of calls might otherwise interfere with each other. For example, a main function might call a helper function to perform a specific task, and the helper function's local variables won't affect the main function's variables. This approach reduces naming conflicts and makes the code more predictable and easier to debug. Recursive functions are functions that call themselves, a technique particularly useful for solving problems that can be broken down into smaller, similar subproblems. The key to recursion lies in defining a base case, which is a condition that stops the recursion and prevents infinite loops. The recursive case then reduces the problem size and calls the function again. For instance, calculating a factorial involves multiplying a number by the factorial of the number -1, with the base case being when the number is 0 or 1. Similarly, the Fibonacci sequence relies on recursion to compute each number as the sum of the two preceding ones. These examples demonstrate how recursion can lead to elegant and concise solutions for problems that might otherwise require complex loops. A practical example of recursion in shell scripting is a function designed to traverse directories and list all files, including those in subdirectories. This function might use tools like ls or find to explore the file system. Each time it encounters a directory, it calls itself recursively to process its contents. To prevent infinite loops, the function must have a base case, such as checking if the current item is a file rather than a directory. This approach is invaluable for tasks like searching for specific files, generating reports, or performing batch operations across a directory structure. By leveraging recursion, the script can handle arbitrarily deep directory hierarchies without requiring explicit loops for each level. When working with recursive functions, following best practices is essential to avoid common issues. First, ensure that every recursive function has a clear and well-defined base case to terminate the recursion. Without this, the function could enter an infinite loop, leading to a stack overflow. Limiting the recursion depth is another important consideration, as deep recursion can consume excessive memory and slow down the script. Using the local keyword to declare variables within recursive functions helps prevent unintended side effects by keeping them isolated to each call. Finally, always test recursive functions with small inputs to verify their behavior before scaling up. These practices ensure that recursion is both effective and safe in shell scripting. Despite its power, recursion in shell scripting comes with several pitfalls. One of the most common is infinite recursion, which occurs when the base case is missing or incorrectly implemented. This can cause the script to crash or hang indefinitely. Another risk is stack overflow, where excessive recursive calls consume all available memory, leading to program failure. Misusing global variables in recursive functions can also introduce bugs, as changes to these variables may affect multiple layers of recursion unpredictably. Additionally, handling arguments in nested function calls requires careful attention, as incorrect parameter passing can lead to unexpected results. Recognizing these challenges and addressing them proactively is crucial for writing reliable recursive scripts. Advanced functions are a cornerstone of efficient and maintainable shell scripting, offering a way to structure code for reuse and clarity. Recursion, in particular, provides elegant solutions for complex problems that involve repetitive, hierarchical, or nested structures. Mastering parameters, return values, and variable scope is essential for leveraging these features effectively. However, the true value of these concepts lies in their application to real-world scenarios. By practicing with examples like directory traversal, mathematical computations, and data processing, you can deepen your understanding and build confidence in using advanced functions. The key to success in shell scripting is not just knowing the tools, but applying them thoughtfully to solve practical problems. Signals are software interrupts that the operating system sends to processes to notify them of specific events. These interrupts act as a way for the system to communicate with running programs, allowing them to respond to user actions, system conditions, or other external factors. For example, when you press Ctrl+C in a terminal, it sends a signal to the current process, typically interrupting its execution. Signals are also used to manage process termination, such as when a program needs to shut down gracefully, or when the system needs to terminate a runaway process. Each signal is assigned a unique number, such as SIGINT, which corresponds to the number 2, and SIGTRM, which is the number 15. These numbers help the operating system and programs identify and handle different types of signals effectively. In shell scripting, several common signals are frequently encountered. The first is SIGINT, which stands for interrupt signal, and is typically triggered by the user pressing Ctrl+C. This signal is often used to stop a running script or process. Another important signal is SIGTRM, short for termination signal, which is the default signal sent by the kill command to terminate a process. Unlike SIGINT, SIGTRM allows a process to perform cleanup operations before exiting. Then there is SIGKILL, which is a forceful termination signal that cannot be caught or ignored by a process. It is used as a last resort when a process is unresponsive. Lastly, SIGHUP, or hang-up signal, is sent when a terminal connection is closed or when a service needs to reload its configuration. Understanding these signals is crucial for writing scripts that can handle unexpected events and maintain system stability. To manage signals in shell scripts, the trap command is an essential tool. The trap command allows you to specify a set of instructions that will execute when a particular signal is received. The basic syntax is trap command signal, where command is the action to take and signal is the signal to catch. For instance, if you want your script to display a message and exit when the user presses Ctrl+C, you can use trap echo received SIGINT exit INT. This ensures that the script responds to the interrupt signal by printing a message and terminating gracefully. The trap command can also be used to handle multiple signals at once, making it a versatile tool for managing various types of interruptions in your scripts. Let me demonstrate some practical examples of signal handling in shell scripts. For handling the SIGINT signal, you might use trap echo cleaning up exit INT. This ensures that before the script exits, it performs any necessary cleanup tasks, such as removing temporary files or releasing resources. Similarly, for the SIGTRM signal, you could use trap echo shutting down, exit term to log a message, and terminate the script when a termination request is received. If your script needs to respond to multiple signals, you can specify them all in a single trap command, like trap echo signal caught, exit INT term. This approach allows your script to handle different types of interruptions with a unified response, improving its reliability and user experience. When implementing signal handling in your scripts, there are several best practices to follow. First, avoid using infinite loops within signal handlers, as this can lead to unexpected behavior or system instability. Instead, ensure that your handlers perform their tasks and exit promptly. Always use the exit command after handling a signal to terminate the script gracefully, preventing it from continuing in an undefined state. Additionally, test your scripts by simulating signals using commands like kill SIGINT PID, where PID is the process ID of the script. This helps verify that your signal handlers work as intended under real-world conditions. By adhering to these practices, you can create more robust and dependable shell scripts that respond effectively to external events. In summary, signal handling is a critical aspect of writing reliable shell scripts. It enables scripts to respond to external events, such as user input, system shutdowns, or process termination requests. The trap command serves as the core mechanism for intercepting and managing these signals, allowing scripts to perform necessary actions before exiting. By properly implementing signal handling, you can enhance the stability, usability, and resilience of your scripts. Whether it's cleaning up resources, logging events, or terminating processes gracefully, mastering signal handling is a valuable skill for any shell programmer. With careful design and testing, your scripts can handle interruptions with confidence and efficiency. Subshells are child processes of the current shell. This means when you create a subshell, it runs as a separate instance of the shell, inheriting the environment variables of the parent shell, but operating independently. This isolation is useful for executing commands without affecting the main shell state, such as temporarily changing directories or modifying variables. Background processes, on the other hand, allow you to run commands in the background without blocking the terminal. This is particularly helpful when you need to perform long-running tasks, like compiling code or transferring files, while continuing to use the shell for other activities. Together, these features enhance the efficiency and flexibility of shell scripts, enabling more complex and modular workflows. Subshells are created using parentheses. When you enclose a set of commands in parentheses, the shell spawns a new subshell to execute them. For example, the command echo hello ls runs the echo and ls commands in a subshell. This is different from running them in the current shell because any changes made in the subshell such as variable assignments or directory changes, do not affect the parent shell. This isolation is powerful for testing configurations, running temporary tasks, or ensuring that certain operations do not interfere with the main shell environment. It's important to note that while subshells inherit the parent's environment variables, they do not share the same history or interactive state, making them ideal for controlled execution. The syntax for running a command in the background involves using an ampersand. When you append an ampersand to a command, the shell executes it in the background, allowing you to continue using the terminal for other tasks. For instance, the command sleep 10 and runs the sleep command for 10 seconds without blocking the shell. This is particularly useful for tasks that take time, such as downloading files or processing large datasets. By running these commands in the background, you can maintain productivity without waiting for each task to complete. However, it's essential to manage background processes carefully, as they may require input or output redirection to avoid unexpected behavior. Job control in background processes allows you to manage and interact with running tasks. The jobs command lists all active background jobs, showing their status and identifiers. For example, if you run a command in the background, jobs will display it as a job with a number. To bring a job to the foreground, you can use the FG command followed by the job number, such as FG%1. This is useful if you need to interact with a background process or check its output. If a job is no longer needed, the kill command with the job number, like kill%1, terminates it. These tools provide fine-grained control over background processes, ensuring you can manage them effectively. Subshells and background processes serve different purposes, but can be combined for advanced functionality. Subshells isolate the execution context, making them ideal for running a group of commands without affecting the parent shell. Background processes, meanwhile, allow commands to run concurrently, enabling the shell to handle multiple tasks simultaneously. When combined, such as with Command 1, Command 2, and a subshell runs in the background, executing a sequence of commands independently. This is useful for parallelizing tasks, like compiling multiple files or running scripts simultaneously, while maintaining the integrity of the parent shell's environment. Understanding when to use each feature is key to writing efficient and scalable shell scripts. Practical use cases for subshells and background processes include running long tasks in the background, such as file backups or data transfers. By executing these tasks in the background, you can continue working without interruption. Subshells are also valuable for isolating temporary changes, like modifying the current directory or setting temporary variables without altering the parent shell's state. For example, a subshell can handle a complex command sequence that might otherwise clutter the main shell. Additionally, these features enable parallel processing, such as compiling multiple source files at once, which can significantly reduce execution time in development workflows. Leveraging these tools effectively can streamline task management and improve overall productivity. Common pitfalls when using subshells and background processes include misunderstanding their behavior. Subshells do not affect the parent shell's environment, which can be confusing if you expect changes like variable assignments to persist. This is a feature, not a bug, but it's important to recognize that subshells operate in their own context. Background processes may require input or output redirection to function correctly, especially if they depend on user interaction or external data. For example, a command that reads from standard input will fail silently if run in the background without redirection. Overusing subshells can also increase resource usage, as each subshell consumes system memory and processing power. It's crucial to balance their use with performance considerations and ensure they serve a clear purpose in your scripts. Advanced techniques for managing subshells and background processes include using the wait command to pause the shell until background tasks complete. This is useful in scripts where subsequent steps depend on the completion of earlier tasks. Combining subshells with pipelines allows for complex workflows, such as processing data through multiple stages in a single command chain. For example, a subshell can handle a series of commands piped into a file or another process, monitoring background jobs with tools like PS or Top provides real-time insights into their status and resource usage, helping you troubleshoot or optimize performance. These techniques empower users to create sophisticated automation scripts that handle concurrency, isolation, and resource management effectively. Subshells and background processes are essential tools for improving shell script efficiency. They allow you to run tasks concurrently, isolate execution contexts, and maintain control over complex workflows. Mastering these features enables you to write modular, scalable scripts that handle multiple tasks without blocking the terminal. Practicing how to isolate tasks, manage job states, and combine these techniques with other shell features will deepen your understanding and proficiency. By applying these concepts in real-world scenarios, you can unlock the full potential of shell scripting, making your workflows more efficient and adaptable to various challenges. A process is an instance of a running program in the shell. When you execute a command, the operating system creates a process to handle that task. The shell manages these processes using tools like PS, top, and kill. These commands allow you to view and control what is happening in the system. For example, PS provides a snapshot of current processes. Top gives a dynamic real-time view, and kill sends a signal to terminate a process. Key concepts include parent and child processes, where a parent process spawns a child process. Each process has a unique identifier called a process ID or PID, which helps the system track and manage it. Processes also have different states, such as running, sleeping, or stopped, which indicate their current activity. Understanding these elements is crucial for effective system management and troubleshooting. Job control allows managing multiple processes in the shell. This feature is particularly useful when you need to run multiple tasks simultaneously. Foreground jobs are those that require your immediate attention and interaction, such as running a command that prompts for input. Background jobs, on the other hand, operate silently without interrupting your workflow. To start a job in the background, you can append an ampersand to the command. For instance, running a long file transfer in the background lets you continue using the shell for other tasks. The FG command brings a background job back to the foreground, while the BG command resumes a stopped job. These tools enable efficient multitasking and help maintain productivity. Managing background processes is essential for optimizing your workflow. To start a process in the background, you can use the ampersand symbol after the command. This allows the process to run without blocking your terminal. The jobs command lists all active jobs, showing their status and associated process IDs. If you need to terminate a job, you can use the kill command with either the job number or the process ID. For example, kill %1 ends the first background job. Additionally, pressing Ctrl plus Z pauses a foreground job and moves it to the background, which is useful for temporarily halting a task and resuming it later. These techniques provide flexibility in handling multiple processes. Signals are messages sent to processes to control their behavior. Common signals include SIGINT, which is sent when you press Ctrl plus C to interrupt a process, and SIGTRM, a polite request to terminate. The kill command can send these signals to a process. For example, kill PID sends a termination signal. However, some processes may ignore SIGTRM, so a more forceful approach is needed. The kill -9 command, or SIGKILL, forcefully terminates a process without giving it a chance to clean up. Other signals, like SIGHUP, can be used to reload configurations without stopping the process. Understanding signals allows you to handle unexpected situations and manage processes effectively. Process priority and nice values determine how the system allocates CPU resources. The nice command sets the priority of a process, with lower values indicating higher priority. For example, a nice value of -20 means the process will get more CPU time than one with a value of 19. The default nice value is 0, but users can adjust it to balance system performance. The renice command allows you to modify the priority of a running process. High priority processes consume more resources, which can impact system responsiveness. By managing nice values, you can ensure that critical tasks receive the necessary resources while preventing less important processes from monopolizing the CPU. Advanced job control techniques enhance your ability to manage complex workflows. The no-hub command allows a process to continue running even after you log out, making it ideal for long-running tasks. The disown command removes a job from the shell's job table, preventing it from being terminated when the shell exits. In scripting, using ampersand and wait commands can manage parallel processes, enabling efficient execution of multiple tasks. For example, starting several background jobs and using wait to pause until they complete ensures synchronization. Monitoring jobs with PS-aux grep process name helps track their status and verify that they are running as expected. These tools provide powerful options for handling intricate shell scripts. Process management and job control are essential for efficient shell scripting. Mastering tools like PS, Kill, Jobs, Nice, and NoHub allows you to handle multiple tasks, monitor system resources, and optimize workflows. These concepts enable you to run processes in the background, adjust their priority, and terminate them when needed. By practicing with signals and job control, you can improve multitasking capabilities and ensure smooth operation of complex scripts. Understanding these fundamentals not only enhances your productivity, but also helps in troubleshooting and managing system resources effectively. Regular practice with these commands will solidify your skills and make you more proficient in shell programming. Optimization in shell scripting refers to the practice of enhancing the performance, readability, and efficiency of scripts. This involves making deliberate choices to ensure that scripts run faster, use fewer system resources, and are easier to understand and maintain. For large-scale scripts, especially those handling substantial data or executing frequently, optimization becomes critical. Without it, scripts can become slow, consume excessive memory, or become difficult to debug. Common optimization goals include reducing execution time by minimizing redundant operations, minimizing memory usage through efficient data handling, and improving maintainability by writing clean, structured code. These goals often require balancing trade-offs, such as choosing between speed and readability. But the end result is a more robust and reliable script. One of the most effective ways to optimize shell scripts is by minimizing command calls. Redundant commands can significantly slow down a script, so reusing variables and results from previous commands is essential. For example, instead of running the same command multiple times, store its output in a variable and reuse it. Replacing multiple commands with a single, more efficient command can also improve performance. For instance, using grep for simple pattern matching is often faster and more straightforward than using awk, which has more overhead. Additionally, setting the option set -e ensures that the script exits immediately if any command fails, preventing unnecessary processing and potential errors from propagating. This practice not only improves reliability, but also reduces the risk of unintended side effects. Leveraging built-in shell commands over external utilities is another key optimization strategy. Built-in commands such as echo, read, and print are executed directly by the shell and do not require spawning new processes, which saves time and resources. For example, using the conditional test is generally more efficient and feature-rich than the traditional test or commands. The operator supports advanced pattern matching and logical operators, making it a better choice for complex conditions. Additionally, avoiding subshells created by command substitution can reduce overhead. Instead, use variables or direct file operations where possible. This approach minimizes the number of processes spawned, leading to faster script execution and lower system load. Efficient loop structures are crucial for optimizing shell scripts, particularly when dealing with arrays or large files. Using for loops instead of while loops for iterating over arrays or lists can be more efficient, as for loops are designed for this specific purpose. However, nested loops can quickly become a performance bottleneck, so it's best to avoid them when possible. For bulk operations, tools like Zargs or Parallel can distribute work across multiple processes, significantly reducing execution time. Pre-computing loop variables, such as calculating values outside the loop body, also helps minimize repeated calculations. For example, if a loop requires a fixed value, compute it once before the loop starts rather than recalculating it in each iteration. These techniques ensure that loops run as efficiently as possible, avoiding unnecessary pipes and redirections can greatly enhance script efficiency. Pipeline chains, such as combining grep and awk, often introduce overhead by passing data through multiple processes. Instead, simplify these chains by using a single command that achieves the same result. For instance, replacing grep awk with grep e can eliminate the need for an additional process. Using exec for file descriptor redirection is another effective strategy, as it avoids repeated open calls, which can be costly in terms of system resources. Additionally, replacing commands like cat file grep with grep file improves performance by eliminating the extra cat process. These small changes can collectively lead to significant improvements in script speed and resource usage. Resource management is a vital aspect of shell script optimization, particularly in environments with limited memory or processing power. Closing unused file descriptors with exec3 and prevents leaks ensuring that the script does not consume unnecessary system resources. Profiling script performance using the time command helps identify bottlenecks, allowing you to focus optimization efforts where they matter most. For memory-intensive tasks, processing data in chunks rather than loading entire files into memory can prevent excessive memory usage. Techniques like while red loops enable this by handling data line by line, making it possible to work with large files without overwhelming the system. These practices ensure that scripts remain efficient and stable even under resource constraints. In conclusion, optimization should always be balanced with readability to ensure maintainable code. While performance is important, overly complex optimizations can make scripts harder to understand and debug. Testing optimized scripts thoroughly is essential to verify that changes do not introduce errors and that performance improvements are genuine. Finally, regularly reviewing and refactoring scripts allows you to adapt to new tools, best practices, and changing requirements. By combining these strategies, you can create shell scripts that are both efficient and easy to maintain, ensuring they remain effective over time. Shell scripts often need to interact with other languages for advanced functionality. This is because no single language can handle every task efficiently. For example, while Shell is excellent for system tasks like file manipulation or process control, it lacks the robust libraries and complex data handling capabilities of languages like Python. Common languages that integrate well with Shell include Python, Perl, Ruby, and C. Each of these languages brings unique strengths to the table. Python, for instance, excels in data analysis and machine learning, while C offers low-level system access. By integrating these languages, developers can create more powerful and flexible solutions. This synergy allows for leveraging the best tools for specific tasks, ultimately leading to more efficient and maintainable code. To call Python from Shell, you can use the Python command followed by the script name and any arguments. This allows you to pass parameters directly from the Shell environment, making scripts more dynamic. For example, if you have a Python script that processes data, you can pass input files or configuration options as command line arguments. Capturing the output of Python scripts is straightforward using command substitution, which is denoted by the syntax. This means you can store the result of a Python script in a variable, or use it as input for another command. For instance, running Python script pyarg1 arg2 will execute the script and return its output, which can then be processed further within the shell. This integration is particularly useful for tasks like logging, data transformation, or automating workflows that require both system-level and high-level programming. When working with Python, you can also invoke shell commands using the subprocess module. This module provides functions like subprocess, run, and system to execute external commands. The subprocess run method is preferred for its flexibility, as it allows you to capture output, handle errors, and manage input streams. For example, running subprocess, run ls. L will execute the ls command and display the directory listing within a Python script. This capability is invaluable for tasks like file management, system monitoring, or interacting with command line tools. Python can also process the output of these commands, enabling you to filter, analyze, or store the results programmatically. By combining shell commands with Python, you can create scripts that handle both system-level operations and complex logic, making your workflows more versatile and powerful. Interprocess communication, or IPC, is a critical concept when integrating shell and Python. Pipes, denoted by the vertical bar symbol, allow you to chain processes together, passing the output of one command as the input of another. For example, you might use a pipe to send the output of a shell command, like ls, to a Python script for further processing. This is achieved by redirecting standard input and output, which are the default channels for communication between processes. Tools like awk or sed can act as bridges, transforming data between shell and Python workflows. For instance, a shell script might generate a list of files, which a Python script then processes to extract specific information. By mastering IPC, you can create seamless data flows that combine the strengths of both environments, enabling more sophisticated automation and data handling. Real-world examples of integration between shell and Python are abundant. A common scenario is a shell script that calls a Python script to perform data processing tasks. For instance, a script might gather log files and pass them to a Python script that analyzes the data and generates reports. Conversely, a Python script might invoke shell commands to manage files, such as compressing directories or checking system resources. Hybrid workflows are especially useful in automation, where tasks like logging, monitoring, or deployment require both low-level system access and high-level logic. For example, a Python script could use shell commands to check disk space and then trigger alerts or backups based on predefined conditions. These examples illustrate how integration enables more efficient and scalable solutions, combining the simplicity of shell with the power of Python. The benefits of integrating shell with other languages are significant. First, it extends the capabilities of shell scripts, allowing them to handle tasks that would otherwise be difficult or impossible. For example, complex data manipulation or machine learning tasks can be offloaded to Python. Second, it enables the use of powerful languages for logic that is too intricate for shell alone, such as handling large datasets or implementing advanced algorithms. Third, integration simplifies maintenance by modularizing code, making each component easier to update or debug. Finally, it improves efficiency by leveraging the strengths of each tool, reducing the need for reinventing the wheel. These advantages make integration a cornerstone of modern automation and scripting, allowing developers to build robust, scalable, and maintainable systems. Integration with other languages significantly enhances the versatility of shell scripting. Python, in particular, is a popular choice due to its simplicity and extensive libraries, making it accessible for both beginners and experts. To achieve seamless workflows, practice using the subprocess module, command substitution, and inter-process communication techniques. These tools allow you to combine the strengths of shell and Python, creating scripts that are both powerful and efficient. As you explore more advanced use cases, consider how integration can solve real-world problems, such as automating complex workflows, analyzing data, or managing system resources. By mastering these concepts, you can unlock new possibilities in your scripting projects and build more sophisticated solutions that adapt to evolving requirements. Automation transforms the way system administrators manage tasks by significantly reducing the need for manual intervention. When we automate, we eliminate repetitive actions that are prone to human error, ensuring that tasks such as backups, monitoring, and user management are executed consistently. For instance, a script can handle daily log rotations without requiring a human to initiate the process. The benefits of automation extend beyond saving time. They include scalability, allowing systems to handle growing workloads efficiently, and consistency, which ensures that processes are performed the same way every time. This reliability is crucial in environments where precision and uptime are paramount. Cron jobs are a powerful tool for scheduling tasks in Unix-like systems, and they rely on the cron tab file to define their execution. The syntax for a cron job is structured as minute, hour, day, month, day of week command, where each field represents a specific time component. For example, a task that runs daily at 2 a.m. would have 02 followed by the command. This flexibility allows administrators to automate critical workflows such as weekly backups, which might be scheduled to run on Sundays at midnight, or hourly system checks to monitor performance metrics. By leveraging cron, tasks are executed reliably without manual oversight, freeing up time for more complex responsibilities. User management is a fundamental aspect of system administration, and shell scripts can greatly simplify this process. Commands like useradd and userdel enable the creation and removal of user accounts, while passwd allows for password management. For example, a script can read a list of usernames from a file and add them to the system, ensuring that each user is created with predefined settings. However, it is essential to include checks to prevent duplicate entries, which could lead to conflicts. By incorporating validation logic, such as verifying if a user already exists using the id command, scripts can handle errors gracefully and maintain the integrity of the user database. Monitoring logs in real time is critical for identifying issues as they occur, and shell scripts provide an efficient way to achieve this. The tail F command allows administrators to track changes in a log file dynamically, while grep can filter for specific patterns such as error messages or failed login attempts. For instance, a script could monitor the auth log for unauthorized access attempts and send an email notification to the system administrator. By automating this process, teams can respond to potential threats or system failures more quickly, minimizing downtime and improving overall security. Backup automation ensures that critical data is protected and recoverable in the event of a failure. Tools like tar, rsync, and cp are commonly used to create backups, each with its own advantages. Tar is ideal for compressing files into archives. rsync efficiently transfers only the changes since the last backup, and CP is straightforward for copying files. For example, a script might compress log files using tar and then transfer them to a remote server using rsync. By scheduling these backups with cron or triggering them on demand, administrators can maintain up-to-date copies of data without manual intervention, reducing the risk of data loss. System resource monitoring is essential for maintaining optimal performance and preventing failures. Scripts can use commands like df to check disk usage, free to monitor memory, and top to assess CPU load. For instance, a script might calculate the percentage of disk space used and send a warning if it exceeds 80%. Similarly, memory and CPU usage can be tracked to identify bottlenecks or resource-intensive processes. By setting thresholds and automating alerts, administrators can proactively address issues before they escalate, ensuring that systems remain stable and responsive. Error handling is a crucial aspect of writing robust shell scripts, as it ensures that failures are managed gracefully. Using if statements, scripts can check the exit code of a command to determine if it succeeded or failed. The set E option automatically exits the script if any command returns a non-zero exit code, preventing cascading errors. Additionally, the trap command allows for cleanup actions, such as removing temporary files, even if the script is interrupted. For example, a script might validate input parameters before executing a critical command, ensuring that only valid data is processed and reducing the risk of unintended consequences. Advanced shell scripting techniques unlock the full potential of automation, enabling complex tasks to be handled efficiently. Arrays allow scripts to manage multiple values, while functions promote code reuse and modularity. Command substitution, using backticks or $, lets scripts dynamically generate input for other commands. Tools like awk, sed, and find extend the capabilities of scripts, allowing for text processing, file manipulation, and searching. For example, a script might use awk to extract specific data from a log file, and sed to modify file names based on a pattern, demonstrating how these tools can be combined to solve intricate problems. In conclusion, automation is a cornerstone of modern system administration, offering significant improvements in efficiency, reliability, and scalability. By mastering shell scripting, administrators can take control of their environments, reducing manual tasks and focusing on strategic initiatives. The key to success lies in practice, creating scripts for daily tasks and refining them over time. As skills develop, so too does the ability to tackle more complex challenges, making automation an invaluable tool in the ever-evolving landscape of system management. Good day. Today, we will explore advanced techniques for editing, searching, and managing files in the shell environment. These methods are essential for handling complex tasks efficiently, especially when working with large datasets or structured text files. Tools like sed, awk, find, and grep are powerful allies in automating and streamlining file operations. By mastering these, you can significantly enhance your productivity and tackle tasks that would otherwise be time-consuming or error-prone. We will delve into each of these tools, their unique capabilities, and how they can be combined to solve real-world problems. Let us begin with sed, a stream editor used for performing find and replace operations on files. For example, the command sed old newbie file txt replaces all instances of the word old with new in the specified file. This is particularly useful for batch modifications, such as updating configuration files or standardizing text formats. Sed also allows you to target specific lines using address ranges. For instance, sed 35's fix g will replace the word with fix only in lines 3 through 5 of the file. Additionally, the I option enables in-place editing, modifying the file directly without creating a backup. This is invaluable when you need to apply changes immediately and efficiently. Next, we turn to awk, a versatile tool for text processing and data extraction. Awk processes files line by line, splitting each line into fields based on whitespace by default. For example, the command awk print $1 file txt prints the first field of every line, which is useful for extracting specific data points. Awk supports variables, conditionals, and functions, allowing you to create dynamic filters and transformations. You can use patterns to match specific lines and actions to perform operations on them. Combining awk with other commands, such as grep or sort, enables advanced data analysis, making it a cornerstone of text manipulation in shell scripting. Now, let us discuss advanced file searching using find and grep. The find command allows you to search recursively through directories, filtering by name, type, or modification time. For example, find. Type fname log locates all log files in the current directory and its subdirectories. This is ideal for managing large file structures. Meanwhile, grep is used for searching text patterns within files. The R option enables recursive searches, such as grep r error var/logs, which scans all files in the logs directory for the word error. To exclude specific patterns, the V option inverts the match, helping you filter out unwanted results. Together, these tools form a robust system for navigating and analyzing file content. Handling large files requires strategies to avoid overwhelming system resources. The split command divides a file into smaller chunks, such as split L1000 file txt output, which splits the file into parts of 1000 lines each. This is useful for processing massive datasets in manageable portions. The tail F command monitors a file in real time, showing updates as they occur, which is critical for tracking log files or live data streams. Additionally, processing files line by line with while-read loops ensures efficiency, as it avoids loading the entire file into memory. These techniques are essential when working with files that are too large to handle in their entirety. Chaining commands using pipes and redirection is a fundamental skill in shell scripting. The pipe symbol allows the output of one command to serve as the input for another. For instance, grep error log txt sort unique analyzes log files by first identifying error messages, then sorting and deduplicating them. Redirection with AND lets you control input and output, such as redirecting command output to a file or reading input from a file. The zargs command further extends this by passing the output of one command as arguments to another, enabling complex workflows. These mechanisms allow you to build powerful, modular scripts that handle data processing with precision. To solidify these concepts, let us examine practical examples. Automating log file parsing might involve using awk to extract timestamps and sed to clean up irregular formatting. Cleaning CSV data could entail removing trailing spaces or invalid characters with sed and awk. For backups, find can locate specific files, Tar can archive them efficiently, creating custom scripts for repetitive tasks, such as renaming files or generating reports. Demonstrates how these tools can be combined to save time and reduce manual effort. These examples highlight the flexibility and power of shell scripting in solving real-world challenges. In conclusion, advanced file manipulation techniques are indispensable for anyone working with shell scripting. Tools like sed, awk, find, and grep provide the means to handle complex text and file operations with ease. By practicing the combination of commands, you can tackle intricate scenarios and optimize your workflows. Applying these methods to real-world tasks not only improves efficiency, but also enhances your ability to manage and analyze data effectively. As you continue to explore these tools, remember that experimentation and practice are key to mastering their full potential. Good day. Today, we will explore the fundamental concepts of packaging and distribution in the context of shell scripting. Packaging refers to the process of bundling scripts along with their dependencies into a single portable unit. This ensures that when a script is moved to another system, all required components are included, preventing errors caused by missing files or incompatible versions. Distribution, on the other hand, involves the methods used to deliver these packaged scripts to end users or systems. Effective distribution strategies ensure that scripts are accessible, up-to-date, and easy to install. Standardization plays a critical role here because it allows scripts to work consistently across different operating systems and environments. Without standardized practices, scripts may fail due to variations in system configurations, libraries, or command line tools. Let's discuss the tools and techniques commonly used in packaging and distribution. First, there are the archiving utilities like tar, which stands for Tape Archive. tar allows you to combine multiple files into a single archive, preserving directory structures. Compression tools such as gzip, bzip2, and xc further reduce the size of these archives. For example, tar combined with gzip creates a tar gz file, which is widely supported. Other tools like RPM and deb are package formats specific to Linux distributions. RPM is used by Red Hat-based systems, while deb is used by Debian and Ubuntu. Version control systems like Git are also essential for tracking changes in scripts over time. This helps developers collaborate revert to previous versions, and maintain a clear history of modifications. Packaging formats vary, including TAR GZ for general use, SH for standalone scripts, and RPM or DEB for distribution-specific packages. Each format has its own strengths and use cases. Now, let's walk through the process of creating a tarball. The basic command is tar cvf package.tar script 1 script 2. Here, the C option creates a new archive, V provides verbose output, and F specifies the file name. To add compression, you can use the Z option for gzip, resulting in a tar gz file. For example, tar czvf package tar gz script 1 script 2. This command compresses the archive while maintaining the original file structure. It's also important to include a readme file in your package. This file serves as a guide for users, explaining how to install, configure, and use the script. Without a readme, users may struggle to understand the purpose or requirements of your script. Always verify that the tarball includes all necessary files and that the compression process works as expected. Next, we'll examine the different compression methods available. Gzip is known for its speed, making it ideal for situations where time is a priority. However, its compression ratio is moderate compared to other tools. Bzip 2, on the other hand, offers better compression, but at the cost of slower performance. This makes it suitable for scenarios where storage space is more critical than speed. XC provides the highest level of compression, often reducing file sizes significantly, but it is the slowest of the three. The choice of compression method depends on the specific needs of your project. For example, if you're distributing a large script and storage is a concern, XC might be the best option. However, if you need to quickly generate a package for a temporary use case, Gzip would be more efficient. Always test the compression method with your files to ensure it meets your requirements. Let's delve into package managers, which are essential for distributing software on Linux systems. RPM packages are used by Red Hat, CentOS, and similar distributions. They rely on tools like RPM Build to create packages, which include metadata such as the package name, version, dependencies, and installation scripts. Deb packages are used by Debian, Ubuntu, and their derivatives, with dpkg serving as the primary tool for installation and management. These package managers automate the process of installing, updating, and removing software, ensuring that dependencies are resolved correctly. Metadata is crucial because it informs the system about what the package contains, what it requires to function, and how to handle it during installation. This reduces the risk of conflicts and ensures a smoother user experience. Now, let's explore the various methods for distributing shell scripts. Manual distribution involves sharing tar files via email, file transfer, or other direct methods. This approach is straightforward, but can become cumbersome for large or frequently updated projects. Automated distribution leverages CI/CD pipelines to build, test, and deploy packages, ensuring consistency and reducing human error. For example, a script can be automatically packaged and uploaded to a repository whenever changes are pushed to a version control system. Repository-based distribution involves hosting packages on servers such as GitHub, Nexus, or private repositories. This allows users to install packages with a single command, making it ideal for enterprise environments or open source projects. Each method has its advantages, and the choice depends on the scale, frequency, and audience of your distribution. To ensure reliable and user-friendly packaging, follow these best practices. First, document all dependencies clearly. Users must know what software or libraries are required for your script to function. Include installation steps in a README or a separate guide to eliminate confusion. Version numbers are critical for reproducibility, allowing users to track changes and roll back to previous versions if needed. Testing your script in isolated environments, such as virtual machines or containers, helps identify compatibility issues before distribution. Additionally, include license files to clarify usage rights and changelogs to inform users about updates and fixes. These practices enhance transparency, reduce support requests, and improve the overall user experience. Conclusion: packaging and distribution are vital for ensuring that shell scripts are portable, easy to use, and accessible across different systems. The methods you choose depend on your target audience, platform, and project requirements. Whether you opt for manual sharing, automated pipelines, or repository hosting, the goal is to streamline the process for users. By adhering to best practices such as documentation, versioning, and testing, you can create robust and reliable packages. Remember, the right approach not only simplifies distribution, but also enhances the overall effectiveness of your scripts. Always stay informed about new tools and techniques to keep your packaging strategies up to date. Welcome to session 38 on version control for shell scripts. Today, we will explore the fundamental concepts of version control systems and why they are essential for managing shell script development. We will also discuss the tools and workflows that enable efficient tracking and collaboration on script changes. By the end of this session, you will understand how version control ensures reliability, facilitates teamwork, and simplifies the management of evolving script ecosystems. Version control is a system that records changes to files over time, allowing users to track modifications, revert to previous states, and manage collaborative efforts. This capability is vital for maintaining consistent and reliable shell script environments. Imagine working on a complex script where a single mistake could disrupt functionality. Version control provides a safety net, enabling you to roll back to a stable version. It also supports multiple users working on the same project, ensuring changes are documented and integrated seamlessly. Why is version control particularly important for shell scripts? Shell scripts often serve as critical components in automation and system management. Without version control, accidental overwrites or deletions can lead to significant downtime or errors. Tracking changes helps identify the source of issues during debugging or auditing. Additionally, version control fosters collaboration by allowing team members to share, review, and merge script modifications. This structured approach ensures that every change is documented, making it easier to understand the evolution of a script over time. The most popular tools for version control include Git, Mercurial, and Subversion. Git is a distributed version control system that has become the industry standard due to its flexibility and powerful branching capabilities. Mercurial is similar to Git, but emphasizes simplicity and ease of use. Subversion, a centralized system, is less commonly used for scripts, but still relevant in certain workflows. Each tool has its strengths, and the choice depends on project requirements, team preferences, and collaboration needs. Setting up Git for shell scripts begins with installation. On Debian-based systems, you can use the package manager with the command sudo apt install git. Once installed, configure your user identity by setting the name and email with Git config commands. This ensures that every commit is attributed to the correct user. Finally, initialize a repository in your script directory using git init. This creates a new version control history, allowing you to start tracking changes immediately. Git offers several essential commands for managing script changes. The git add command stages specific files for the next commit, making them part of the version control history. The git commit command saves these changes with a descriptive message, capturing the state of the files at that point. The git status command provides a quick overview of the repository's current state, showing which files are modified or staged. Lastly, the git log command displays the commit history, helping you trace the evolution of your scripts. Adopting best practices for shell script versioning ensures smooth and efficient workflows. Commit small, incremental changes rather than large, sweeping updates. This makes it easier to identify and isolate issues. Use a git ignore file to exclude temporary files, logs, or environment-specific data that should not be tracked. Label significant releases with version tags, such as V10, to mark stable points in your script's development. Always maintain a README file to document script functionality, dependencies, and usage instructions. Collaborating with others using Git involves several key steps. To begin, clone a repository using the git clone command, which creates a local copy of the project. For new features, create a branch with git branch feature, allowing you to work independently without affecting the main code base. When ready, merge your changes back into the main branch using git merge or pull. If conflicts arise, resolve them manually by reviewing the differences and selecting the appropriate code. Tools like merge managers can assist in this process. Avoiding common pitfalls is crucial for effective version control. Never edit scripts without committing your changes first, as this can lead to lost work. Refrain from storing sensitive information, such as passwords or API keys, in version control. Always review changes before committing to prevent unintended modifications. After merging, test your scripts thoroughly to ensure that new changes do not introduce errors. These practices help maintain a clean, reliable, and secure version control environment. In conclusion, version control is a cornerstone of reliable shell script development. Git provides robust tools for tracking, managing, and collaborating on script changes. By following best practices, you can enhance productivity, reduce errors, and ensure that your scripts remain maintainable over time. Embrace version control as an essential part of your workflow, and you will see significant improvements in both individual and team-driven script development. Good day. Today, we will explore the world of real-world shell scripting. Shell scripts are not just for simple tasks. They are essential tools for solving practical problems in system administration, automation, and data processing. Imagine a scenario where you need to manage a large server infrastructure. Without automation, tasks like backups, monitoring, or data analysis would be time-consuming and error-prone. Real-world projects demand scripts that are robust, meaning they handle unexpected situations gracefully. They must be reusable, so you can adapt them to different environments, and adaptable, so they can evolve with changing requirements. In this session, we will look at industry-standard examples and personal workflows that demonstrate how shell scripts can streamline complex processes. Let's dive into our first project, an automated backup script. This script ensures critical directories are backed up using tools like tar and rsync. Tar creates compressed archives, while rsync efficiently copies only the changes, saving time and bandwidth. To keep track of backups, we use timestamp-based naming, such as backup 202,310,151,430, tar GZ, which helps in version control. By integrating with cron, a time-based job scheduler, the script runs automatically at specified intervals, ensuring consistency. But what if the backup fails? We include error handling, such as checking exit codes and logging failures, so you can quickly address issues. This combination of automation and reliability makes the script a cornerstone of data protection. Next, we examine a system monitoring script. This tool continuously checks disk usage, CPU load, and memory consumption. Commands like df, top, and free provide real-time metrics. If any of these metrics exceed predefined thresholds, the script sends alerts via email or syslog, ensuring you are notified of potential problems. For example, if disk space is running low, an alert can trigger a cleanup process. The script also logs all results to a centralized file, which is invaluable for auditing and troubleshooting. By having a historical record, you can analyze trends and make informed decisions about system optimization. Our third project focuses on file organization automation. This script sorts files into directories based on their types, such as images, documents, or code. Using find, we locate files, and MV moves them to the appropriate folders. Case statements allow for flexible classification, like handling different image formats. To avoid duplicates, the script calculates file hashes with SHA-256 sum and compares them before moving. A dry run option lets you test the script without modifying files, ensuring it works as intended. This automation not only organizes your files, but also reduces the risk of accidental overwrites or data loss. Now, let's discuss a data processing pipeline. This script processes log files to extract specific patterns using grep and awk. For instance, it might filter out error messages or track user activity. awk helps aggregate data, such as counting occurrences or calculating averages, which is essential for generating reports. The output is formatted in CSV or JSON, making it easy to import into other tools like spreadsheets or databases. SED is used for text manipulation, such as replacing placeholders or cleaning up log entries. This pipeline transforms raw data into actionable insights, demonstrating the power of shell scripting in data analysis. The next project is a security audit script. This tool scans for insecure file permissions, such as world-writable directories, and checks open ports using tools like netstat or nmap. It also verifies outdated packages with apt or yum, ensuring your system is up to date. Once vulnerabilities are identified, the script generates a report detailing the issues and suggesting remediation steps. For critical patches, it can automate updates, reducing the window of exposure. This script acts as a proactive defense, helping maintain system integrity and compliance with security standards. Let's now review best practices for real-world scripts. Modularity is key. Using functions breaks scripts into manageable parts, making them easier to test and reuse. Comments and documentation are vital for others or your future self to understand the script's purpose and logic. Validating input ensures the script handles unexpected data gracefully, while error handling prevents crashes. Testing in controlled environments before deployment avoids disruptions in production. These practices transform a simple script into a reliable, maintainable tool that stands the test of time. Every script has potential pitfalls. One common issue is overlooking edge cases, like empty files or missing directories, which can cause unexpected behavior. Hard-coding paths or values limits flexibility. Instead, use variables or configuration files. Security risks, such as executing unsafe commands or exposing sensitive data, must be addressed. Finally, testing across different OS versions ensures compatibility, as commands and paths can vary. By anticipating these challenges, you can write scripts that are both effective and resilient. Conclusion: shell scripts are powerful tools for automating real-world tasks. Whether it's backing up data, monitoring systems, or processing logs, they save time and reduce errors. Practical projects require careful planning, rigorous testing, and adherence to best practices. As technology evolves, continuous learning ensures your scripts remain relevant. By applying these concepts, you can streamline workflows, enhance system efficiency, and unlock new possibilities in automation. Thank you. Today, we will review key shell programming concepts to solidify your understanding of the foundational elements. This includes understanding how to interact with the command line, manage processes, and manipulate files. We will then apply these skills to a real-world capstone project, which will challenge you to think critically about solving practical problems using shell scripts. Developing a self-contained, efficient script means ensuring it operates independently without external dependencies, while also optimizing for performance. Finally, we will explore troubleshooting and optimizing complex scripts, which involves identifying and resolving bugs, as well as refining code for clarity and speed. To begin, we must define a clear problem or task that your script will address. This could range from automating system backups to processing log files. Your script should incorporate user input, which might involve command line arguments or interactive prompts. File manipulation is essential, so we will discuss techniques like reading, writing, and modifying files, implementing error handling, and logging ensures your script can gracefully handle unexpected situations and provide useful feedback. Finally, we will emphasize the importance of making your script portable across different systems and ensuring the code is readable for collaboration. The tools you will use include a Unix or Linux terminal, such as Bash or ZSH, which provides the environment for executing scripts. Text editors like Vim, Nano, or VS Code will help you write and edit your code efficiently. Version control with Git is crucial for tracking changes and collaborating with others. Testing frameworks like SH Unit 2 or BATS allow you to validate your script's functionality through automated tests. These tools collectively ensure your development process is structured, reliable, and scalable. The development process starts with planning your script's logic and flow. This involves mapping out steps and decision points to ensure a logical sequence. Writing modular functions promotes reusability, making your code easier to maintain. Integrating command line arguments and options allows users to customize the script's behavior. Testing each component incrementally ensures that issues are identified and resolved early, leading to a more robust final product. Advanced shell techniques will enhance your ability to handle complex tasks. Using arrays, loops, and conditionals allows for dynamic and flexible scripting. Regular expressions enable powerful pattern matching for text processing. Signal handling and traps ensure your script can respond to interrupts or errors gracefully. Combining commands with pipes and redirection streamlines data processing, making your scripts more efficient and versatile. Debugging and testing are critical for ensuring your script works as intended. The Set X option traces command execution, while Set E exits on errors, helping you identify issues quickly. Validating input and handling edge cases prevents unexpected failures. Writing test cases for all functionalities ensures reliability. Using Echo and Logger for diagnostics provides visibility into the script's behavior, making it easier to troubleshoot problems. Documentation is essential for making your script accessible to others and for future reference. Adding comments to complex logic clarifies the purpose of specific code sections. Including a usage or help function guides users on how to interact with the script. Following PEP 8 style guidelines for shell scripts ensures consistency and readability. Documenting dependencies and setup instructions helps others replicate your environment seamlessly. Common challenges in shell scripting include syntax errors, which can be avoided through careful code review, and permission issues, which require proper file access settings. Solutions like peer testing and iterative debugging help refine your work. Cross-platform compatibility requires using standard commands and avoiding OS-specific features. Optimizing performance for large datasets involves techniques like minimizing resource usage and leveraging efficient algorithms. Before submission, we will verify your script's functionality by testing all edge cases and ensuring it behaves as expected. Code clarity and maintainability are prioritized through clean structure and comments. Submitting the script with a README file provides essential information for users. Finally, presenting your project to peers or instructors offers valuable feedback and demonstrates your ability to communicate technical solutions effectively. In summary, this course has equipped you with essential shell programming skills, from basic commands to advanced techniques. Practicing through projects is vital for mastering these concepts. Exploring automation and DevOps opens opportunities to apply your skills in real-world scenarios. For further growth, consider advanced topics like scripting with Python or integrating scripts into CI/CD pipelines, which expand your capabilities in system automation and software development. And just like that, our dreamy coding adventure has come to an end. I hope the gentle ebb and flow of the tutorial, combined with the tranquil melodies, have left you feeling both informed and at ease. Whether you managed to catch every line of code or drifted off into a peaceful slumber, remember that the world of shell will always be here waiting for you. Keep your code clean, your mind open, and your spirit relaxed. Don't forget to subscribe to Code Snooze so you never miss out on another soothing coding journey. Hit that like button if this video brought you a moment of calm and learning, and share it with fellow coders or anyone in need of a serene study session. Thank you for joining me in this cozy corner of the internet. Until next time, may your code run smoothly and your dreams be filled with brilliant algorithms. Sweet dreams, sleepy coders.